think I'm gonna try to stay more than 1 hour and a half. It's gonna depend on how tired I get by reviewing the articles, but I wanna review all the articles today. And I think I'm gonna change all the text from ChatGPT because I think that if I just leave the text from ChatGPT, even though I can review and make sure if it's correct, that it is correct, I don't think it's gonna rank because of the Google's AI identification system. So I think it's better to just use ChatGPT as a template and then remove the text and and write on my own style, let's say. I can say pretty much the same thing, but from whatever comes up off the top of my head. And yeah, the thing is that obviously sucks is that there is gonna be a lot of people that are using ChatGPT and that are flooding the internet with this. That like you're kind of forced to use these AI tools because everyone's gonna use them. That's the problem. And then obviously there already is a lot of paid tools that people are gonna spend thousands of dollars to write the articles as well. And then you're gonna be competing with all of those people. And because they can use AI, they are gonna mass produce a bunch of articles on every single topic. So that's the thing that I don't know, like how do you compete against that if you don't have it? And I don't know a good answer. I think that the best that I can do now with what I have is just to use ChatGPT. Also, I've seen that ChatGPT, they're gonna start charging $42. And I think the reason for 42, specifically 42, has to do with the Galaxy movie, the Rich Har I forgot how to say that, but the movie where they ask the computer what's the meaning of life, and then it says 42, so it's probably because of that. But yeah, since they're gonna charge for $42 for ChatGPT, I still have the free version. I'm gonna try to make as much articles as possible with ChatGPT as a template, like I said, and I'm gonna after I create all the templates, or as I create the templates, I'm gonna create a funnel where I start reviewing them, and I'm gonna post the templates on another folder for the articles. So yeah, I think the best thing that I can do to compete and with all the people that are gonna be using a bunch of AI is to do it like this, where it's kind of a balance between using AI and my own view on things, because that's gonna be hard to do for other people because you can't mass produce something that is unique, which is your own view. And then I also was reading or looking at a bunch of things about copyright, and that's also a thing that I'm very confused about, and I really don't know like what to make of it because in my mind, so for example, if I use an algorithm from another site, like say Breath First Search or from ChatGPT, like is that copyright content or not? And I think that it would be pretty stupid to be copyright content because the algorithm was created. That would be like saying that if you use the word they, then you're copywriting someone because someone else already used that word on their site. It wouldn't make any sense. So obviously that's a ridiculous example, but you can see that there's the gradient of things that are allowed, you are allowed to do, and then as the context, as it creates a context that creates the meaning of whatever that is, then it becomes a copyright content. But then the issue with that is obviously that is gonna be subjective, and that's the problem because it's impossible to tell at some point if you're using copyrighted because there's only so many ways that you can say the same information in different ways. And that's the problem with the whole AI thing. Like, even if they detect AI tools and what's going to be the determining factor just to know if someone's copywriting or not. And that's a problem because obviously I want to do the right thing, which is to create my own content authentic. But then that's obviously also stupid if you follow that, because then you're just gonna lose to people that are not doing that and they're just using AI at mass. So it becomes one of those things where there's nothing I can do about it. Like I have to use the AI and I have to do things like this because the system forces me to follow this path. Otherwise, I'm just gonna not be able to compete with people that are doing these things. So I'm gonna run the risk here of using ChatGPT as much as I can and just changing enough so that I can rank on the on SEO. And then we'll see what happens. Obviously, even doing all that, you're still in a disadvantage because there are a lot of people that have the paid AI systems that are not going to be able to be detected. People are not going to be able to detect those AI systems because at some point, it's like a lot of these language models already passed the Turing test. And I think it is also somewhat questionable to think about the ones that are probably the most powerful, that they're not released to the public, if they are conscious or not. This is still something that is impossible to tell because nobody knows where consciousness comes from. So you can't argue either way, so there's no way to know if the algorithms are conscious or not. And then you can think about, like, you can say that this is ridiculous because it doesn't make sense that a bunch of if-else statements on a computer or functions would be conscious. But then if you think about it, what is a human being? Where do you draw the line of what makes up what you think you are from everything else? Because if it wasn't for the water you drink or the air you breathe, you wouldn't be thinking. And if it wasn't for all the amino acids in your body that make up the proteins and the fats and all the carbohydrates that make up the glucose, or all this biochemistry in your body, you wouldn't exist. And that's obviously correlated with the planets, the sun, and everything else. So at what point do you say that a decision you make is because you were making the decision and it's not all the interactions of the universe that are happening in order to make you do the decision? I think it's a lot more likely that your ego doesn't have free will because it's just a consequence of cause and effects relationships that create everything in the universe, that creates who you are, and the boundary between your body and everything else is the illusion of awareness, which is a frequency of computation that creates the structure of space-time, which is the connection between the electromagnetic field and space-time. So I think that free will exists, but is a gradient, is a distribution, and the only God, which would be what people call God, which would be the most decentralized layer of the identity, of the structure of identity, which is what we call universe, what it is perceived to be outside of you, from the point of view of the ego, which is the singularity point that creates the illusion, which is a hologram. That's, to me, God is the distribution of that, which is the universe and the ego identity. And the identity itself doesn't have free will because it's a byproduct of all the connections between different things that are happening to make up your decision. So following the same logic, you can see that it's impossible to tell if an algorithm is conscious or not because you don't know where to draw the line of, because it is an abstract thing. How would you define the body of an algorithm? You can say that the internet is alive because from one perspective, from one scale of observation, the human beings are the molecules that create the conscious being that is the internet, that is this structure of connections between different agents interacting. And if you think about a body, it's the same thing, where at one layer you have what you consider to be the self and the identity and the ego, which is the conscious structure of abstraction that makes up what the person thinks they are. But on another level, you have trillions of cells interacting and building and destroying things in order to make the whole harmony that creates the system. which is the body. So nobody knows exactly if these algorithms are alive or not, or what does it mean for an algorithm to be alive. And also the other thing that it really doesn't make any sense to me is that how can you say that using ChatGPT content is copyrighted? It's copyright content because ChatGPT is the owner of the content. But the only way for ChatGPT to be the owner of the content is if you scrape the whole web and you force people to give their data. Because obviously you can make the dumb argument that you can decide to not participate in the internet, and you're complying with the rules and you're accepting people to use your data because you are accepting the rules. But that's obviously a stupid argument because it's a fake choice. I can tell you, you can either give me 99.99% of the data, or you can give me 98% of your data. And then I can claim that I'm giving you a choice, but obviously that's dumb because you don't have any choice. It's kind of like you're forced to participate. So, and Google and Microsoft, I think that Microsoft that owns, I think, OpenAI, or at least is a very big investor, and that's what pretty much they did. They bought GitHub, and then they got all the code from people. So they are obviously, and also Google as well, if you think about it, because all of these companies are doing is just extracting all of the data that everyone else creates, and then they're not giving them credit, and they're creating these super powerful AI models built on top of that. But then if you want to use the powerful models they create and they are selling you, they're selling them to you, then you can't use the content because it's copyright. Like, think about how stupid that is. But the reason why things are like that is because of the system. It's not the company's fault, because it's just the structure of their market economy. Everyone is forced to comply with that or to follow these rules, because if you don't do it, someone else is going to do it. So, and then if you allow them to do it, then they gain power over you, and then they can control what you do. So everyone's forced through the natural equilibrium of the market economy to comply. And because the regulatory systems are dumb and slow, then it's not strong enough to contain that. So I'm gonna start from the beginning, from the I always don't know how to say the name of this guy. Dijkstra's. Dijkstra.
Dijkstra. Dijkstra.
Dijkstra. Yeah, I'm gonna start through this guy here. So after I finish all of this that I already did, I'm gonna post the other ones on this resources folder, I think. And here I created this list here to know which ones I'm gonna do next. It might be better to just create a bunch of articles and then post them. Like, just do a simple review first, like I was doing before, to see if the stuff that is on the right article is correct, and then like mass produce them and then post them, everything after doing the simple review, and then only after that I review further. I think that might be a better strategy, because then it increases the probability that I'm gonna capture traffic as I review the articles deeper and I change them to be more personal to how I would write. But it's still a very tricky thing, because I don't know, like, after you read the text and you know what it is, like, because there's only so much things that you can change, and I'm not sure how I'm gonna go about it, because it's quite difficult. I think I'm gonna create, yeah, Do I create a file, a folder for each, or do I one folder for all of them? I think I'm gonna create only one folder for all of them. Or actually, it's gonna be trees because graphs I already did. Yeah, I'm gonna create the same folder structure actually. So whatever I create on the project, I'm gonna be creating there. So I'm gonna mimic this thing here after I finish with all these articles that I have. And once I have, I think, around 100 posts or maybe more, then I'm gonna focus on the merge section, which I'm gonna have to study the API from Printify to integrate. And also gonna think about search other affiliates and think about other ways to make money. I put this thing here, I found this thing as well that allows you to do the typing animation thing, and it's pretty simple, so I was really happy about that. You just have to download and import the library. Is very, very simple. So here you put the delay, then if you want the text to loop, and then you put whatever text you want to show up here. I was thinking about whether or not, I was thinking about that I should add something here, but then I forgot. If I remember, I'm gonna write down. And also, I don't know if I added this before, but now I added to, so that you have the option to go back one page or go back to the main category. Because it's annoying to not have that.
Dijkstra's. Introduction to Dijkstra's algorithm. Dijkstra's algorithm, named after its creator Edsger W. Dijkstra, is a popular algorithm used for finding the shortest path between two nodes in a graph. The algorithm is widely used in many fields, such as computer science, transportation engineering, and operations research. In this article, we will explore the basic concept of Dijkstra's algorithm, how it works, and its various applications. What is Dijkstra?
So like, for example, in this thing here, how I'm gonna create anything different than this? And I guess I've seen a lot of videos as well of people using different AI content systems that they allow you to change, but that also feels weird to use because yeah, you're using the same thing, like, because the main point, I guess the reason why I feel weird about that is because the main point of using that is not coming from a place where you're concerned about the content. It's more coming from a place of how can I hack the algorithm, and that's not the way that I think about it. Yes, the way that I want to approach things is that I want to read the content, and then I want to know if it's going to be helpful or not, and if it's going to be accurate or not. Like, that's what matters to me, is the value in the content, not whether or not it's going to be detectable by AI. But obviously it makes sense from their point of view to try to detect it, because also that's another thing that I was thinking about yesterday, I think, which is that, like, if you think about it, why is spam a bad thing? Why is people using bots a bad thing? And the reason why, I think, is because bots magnify a person's point of view on life. So, and because a person's point of view is not scalable, because that's the whole thing that I was talking about the nature of the collective consciousness and wisdom. Like, wisdom and the intelligence of the collective consciousness is the neural network of human beings interacting with each other in order to update the state of things in relationship to the environment. And that's what creates everything that we have, the systems we have. So it updates through the nodes of the systems, which are the bodies, which are electromagnetic fields, and that produce computation and becomes abstraction, and that's the identity of the collective consciousness, which creates culture and changes the language itself as well, because the language is the process of this flow of information from the electromagnetic fields that is fitting the environment and creating technology based on that. So it creates this feedback loop system. So the reason why spam is bad and the robots, using a bunch of robots is bad, is because it's like what you're doing is increasing the power of one node of the network exponentially. And because you're increasing the power without changing the structure of the geometry of the computation, then it becomes unbalanced because it becomes short-sighted and becomes delusional. And I think that's the core issue of the robots. The problem is not the amount, I think, because if you think about it, there's billions of people on the planet and there's already a ton of information, but then nobody complains about too many people posting things because we assume that should be normal, let's say. So for example, a random person that doesn't have any followers posting stuff that they like about, but nobody cares. Like nobody pays attention to that. And even though there is hundreds of millions of those people, like nobody cares and it's not a problem. But it becomes a problem when you have an entity or an identity that magnifies itself in order to pass a specific message. And that's the issue, I think, the core issue, because they are amplifying the computational power in relationship to the identity structure that they have, but they are not changing the nuance of their identity structure in order to change the geometry of the computation that they are making to make it more sustainable and scalable in relationship to space-time. And that's the issue with freedom of speech as well, because the more influence you have, the more your speech changes the structure of reality through this process of information flow. And because of that, then you have this problem with the speech, and that's the reason why I think that Elon Musk said that you can have freedom of speech but not freedom of speech, because he understands that the gradient of power in relationship to speech is what creates the problems. But then you still didn't solve the problem, because it's a deeper problem than that. Because if you decrease freedom of reach as well, it's like, in fact, the same thing. You're doing the same thing, but in a different way. Like if you could mute someone from speaking in real life, and you just did that, then nobody would listen to what they say. Then you can say, well, they can still have the freedom of speech to say whatever they want, but it doesn't matter because no one is listening. So you're essentially doing the same thing, but you're just rebranding the issue, which is understandable. But the problem is more fundamental, is that we don't understand the connection between cause and effect relationships based on the information flow of the structure, and how it's going to change the geometry of the collective consciousness that is going to produce technology in relationship to space-time, and change the cause and effect relationships of the feedback loop system that may or may not become unsustainable because through the exponential rise of power. So this gradient between the reach of speech and the amount that it changes, I think, is the essence of the problem of the span. And what's happening here with these AI models is that because everyone's going to be using them, it's going to become more spam, and it's going to become this self-fulfilling prophecy. And that's the reason why they're trying to avoid that. They don't want that to happen, to rank, because the natural consequence of that is going to be a delusional state of the collective consciousness, which is going to become self-destructive. Because everyone is always perpetuating the same thing, because they're trying to gain more power. And that's the fundamental problem with the market economy. But then the counter argument to that is the stuff that I was talking about the other day, which is the density of the informational structure that creates the self-fulfilling prophecy. Because if the AI is good enough to integrate a perspective or an identity that encapsulates the variation of all the possible relationships between data and computation, relationship to the environment that creates technology, so that it doesn't disrupt the system, and let's say that it is harmonic by nature, because there's so much information that is diverse and centralized to the proportion that it needs to be in relationship to the context in which it exists, then it doesn't matter if you scale, because the system itself is a natural equilibrium between all the possibilities given the current state of computation and the scientific paradigm in order to be sustainable in relationship to the differences in geometry in space-time. But obviously that's not going to be the case because space-time is irreducible. Like there converges through infinity at some point. But then, like I said before, I think you can create something that approaches the limit of what's computationally reducible so that you can reach the maximum optimal approach in relationship to the current paradigm of knowledge that creates the informational structure that you're perceiving reality from. And then from that point, it would be impossible to come up with a better solution from any paradigm because that would be outside of the power of knowledge itself. Because you can't compute more than that. But I think that that's not what's happening now. I think that nobody knows, nobody has coordination, and nobody could figure out a way to, because the system is too complex. And that's the thing that concerns me the most about what's happening now, is that people don't understand that it's like what happened with Facebook as well, with the echo chambers that is still happening today, and how that increases polarization and increases conflict, which might lead to war, is that people don't understand the side effects of these things. Like there's the third and higher order consequences. Everyone pays attention to the stuff that is immediate and now, but people don't see that this stuff is going to have a very big impact on the way that life is perceived by everyone in the very near future, I think.
What is Dijkstra's algorithm? Dijkstra's algorithm is a graph search algorithm that solves the single source shortest path problem for a graph with non-negative edge weights, producing a shortest path tree. This means that the algorithm can be used to find the shortest path between a single source node and all other nodes in the graph. The algorithm starts at the source node and explores all of its neighboring nodes. It then chooses the node with the smallest distance from the source node and continues to explore its neighbors. This process is repeated until the destination node is reached. How Dijkstra's algorithm works. The basic idea behind Dijkstra's algorithm is to maintain a priority queue of nodes to be visited, with the priority being the distance from the source node. The algorithm starts by initializing the distance of the source node to be 0 and all other nodes to be infinity. The algorithm then explores all of the neighboring nodes of the source node and updates their distances if a shorter path is found. The process of exploring neighboring nodes and updating distances is repeated until all nodes have been visited or the destination node is reached.
Actually, I just thought about a new strategy. I think that's going to be better because honestly, reading this stuff for me is just too hard to come up with something on my own that doesn't have anything to do with the stuff that is already here, because when I'm reading this stuff, to me, it seems already accurate. So if I'm gonna reconstruct this, like using my own words, it becomes very hard to do that, because I would, like, how I'm gonna change the stuff that is being said without changing without while still maintaining what is being said here. So obviously, I think I can do that, but then the issue is that in order to get that authenticity, it's gonna decrease the quality of the content, because then I can't come up with. It's not that I can't come up because I don't know. It's just that I can't come up with things because I'm gonna have to think about how it's gonna be perceived through the AI algorithms. Like, how am I going to know if what I'm writing is going to be considered as AI or not by the AI algorithms? Because there's no understanding of the distribution of what makes something human and what makes something AI. And obviously, I don't have access to all the algorithms and the way that they deduce this information, because also the problem with that is embedded into the algorithms, there is a bunch of assumptions that people make because of the way that the algorithms work. As far as I know, obviously I don't know all the models, but I know some of the fundamentals of the way that these algorithms work, which is through gradient descent and to minimizing the cost function in relationship to a data set. But you're gonna have a bunch of assumptions built in on these algorithms as well, because nobody understands what the language model is doing under the hood, because it's connecting billions of data sets of words and then coming up with a geometrical structure of weights and biases that is gonna allow it to give the best output that it can as possible in relationship to that data set. But then who judges what's the best output as possible? Because truth is always going to be relative to what is considered to be a lie. Because the way that I think right now, that I believe the way that reality works is that you have truth, which is matter, and lies, which is potential. And matter is information as well, because information is the connection between the electromagnetic field and space-time. So the structure of truths and lies is a gradient of distribution that makes up the multifractal structure of matter in space-time. So what that means is that whatever is considered to be truth is always relative to the present moment, and the present moment is through the lens of knowledge and abstraction, is the illusion of cause and effect relationships between the past and the future, because the past and the future don't exist. They only exist through the abstraction that is being experienced by a reference frame in the present moment in time. So that reference frame creates the informational structure that we call matter, and that's considered to be the truth. And then as time passes, which is also part of space-time, then that geometry changes in relationship to the potential that creates the increase in entropy in relationship to the reference frame that is experiencing reality. The frequency of that change is determined by the law of gravity, which in my worldview is awareness. So awareness is God, and it changes matter through the distribution of gradient that makes up the identity, which is the flow from the singularity point that is the ego to the infinite point that would be considered to be as God, but in reality the whole structure is God. So maybe I can draw this stuff. It's like a funnel. So here would be the ego, and then here would be what is considered to be as God, which is the infinite amount of potentials that exist. And the ego is a singularity point that parses the infinity in relationship to an awareness that creates the multifractal structure of space-time, which is this connection between the electromagnetic field, which are relative polarities that create relativistic paradoxes that make up what space-time is. And the change of that field is determined by the awareness, which is a frequency. And a frequency of computation, because it's the relationship between space-time and the electromagnetic field. And then the density of the computation, which is the density of space-time, determines the informational structure of that identity that creates the illusion, which is a hologram of the self. But this comes back to this, I think. Obviously, I have no idea if this stuff is true or not. It's just the way that I'm thinking right now. So it goes from the ego to the infinity, and then from infinity to the ego, creating the self-fulfilling prophecy, which is the structure of knowledge and the nature of the present moment. And that is, the whole structure is a multifractal, which is a self-referencing frame, which always converges to a paradox, because the equilibrium is an illusion, but it exists because the nature of perspective itself is this multifractal structure of polarity that we call the electromagnetic field. So I forgot what I was saying before. I lost my train of thought there. I was gonna say something. I think I'll continue reading, then maybe I'll remember later.
The process of exploring neighboring nodes and updating distances is repeated until all nodes have been visited or the destination.
I think I was talking about the strategy that I'm going to implement, but I was going to talk about something else that I just forgot. But I think the strategy that I'm gonna make here is that for this kind of content, I'm just gonna use AI and I'm gonna fact check. So use ChatGPT, create the whole text with ChatGPT, then read the text the text created. See if I have any questions. If I have questions, I can use ChatGPT and Google to answer those questions and improve the article. But I'm not gonna change the article itself. I'm just gonna fact check to see if there's a high probability that it is. Oh yeah, I was talking about truth and lies. That's what I was talking about. So that's the fundamental issue that I see with the machine learning model and the structure, because what a machine learning model is doing is just capturing the density of data in relationship to what is perceived to be true based on the computation that it does, I think. So there's no inherent truth or lie in the universe. You can say from a meta perspective that the absolute truth is the realization of the relative paradoxes that encapsulates all of them, because you have the understanding that is always relative. So, and that's the reason why I say that to me the highest form of truth is a paradox, is a singularity point that contains all the relative multifractal, or all the relative paradox that are a multifractal structure. Because the paradox encapsulates this notion that you are able to see the distribution of this gradient that makes up the relativistic points of view. And the meta perspective is the highest form of truth that you can get through knowledge, because it is like something metaphysical. But that is not, I don't think that's computationally achievable. Maybe it is actually, if I think about it, because all the, at least we assume that all that you're doing when you think is computing. So is the structure of your electromagnetic field over a geometry creating that perception. So maybe it is computable, but the question is how I don't think, but I'm not really sure, to be honest. But that's the challenge, though, is that how do you determine that the algorithms, the machine learning models, are getting close to the highest approximation of considered to be true in the present moment in time, so that they don't get into this self-fulfilling prophecy, which is going to be this narrow perspective of what everything is. And the way that I think you do that is by understanding the multifractal essence of the field of space-time from which the computation is being done. Because if you do that, then you can have the highest degree of breadth of knowledge that allows you to encapsulate the whole design, let's say, of the infrastructure itself, which means that it doesn't matter if you amplify the output, because the output is, in the amplification of the output, is already integrated the multifractal structure. So it's not really like you're amplifying, you're just, yeah, but that's the thing, because it would go against the nature of the thing itself. I think that's the fundamental problem. Like, it doesn't matter how you go about it, because I think that's the fundamental question, like, where does data come from? Because the data is shaping the algorithms, so the algorithms are always going to be a byproduct of the interaction of data. So I think that the question that needs to be asked is, what is the density of data that you need to have in order for a machine learning model to be, I don't know what's the relationship, but if it's an inverse relationship or direct relationship. I think is a direct relationship, because the more data you have, the closer you can get to some form of truth in relationship to that data. So yeah, I think that as long as the nature of data is spread enough that it contains all the possible perspectives, and those possible perspectives are grounded into a very high density of informational structure, then you can say that by using AI and getting into the cycle of self-fulfilling prophecy because the AI is overfeeding the data. It doesn't matter because the data is decentralized enough that is not going to cause some lack of alignment with the overall computation of the collective consciousness in order to adapt towards a new environment. But the key fundamental issue here is that the metaphysical paradigm that I just talked about, because you can always have new data coming up, and then how you're going to predict that the new data that comes up, I guess that's the question. That's the fundamental question. Is how do you construct something that it doesn't matter if new data comes up, because that thing is able to update itself in relationship to the data in a way that's balanced. And I think that's the question of politics, because it is a spectrum of the electromagnetic field that makes up the nature of the collective consciousness that creates this updating mechanism that human beings do in relationship to the environment that makes us create the market economy and politics in order to bootstrap an informational system that is going to allow us to dominate the environment based on set of behaviors. And we do that through archetypes that we pass along the generations. But the issue is with that system is that system is not balanced. And I think that AI is not built on top of a system like that, at least that I know of. So I think that, and this is the fundamental problem, I think, because AI is not built on top of this system, it's going to create the self-fulfilling prophecies, and it doesn't have a way to compute the Nash equilibrium because it's not built inside of the models. The models are super powerful, and they are being built on top of a computation mechanism of the collective consciousness that is unbalanced, which is the relationship between the market economy and in politics, which leads to natural polarization of the structure, which leads to the corruption of the structure and self-destruction. Because there's no integration of the regulation is not efficient enough to update the frequency of movement from left to right across space-time to achieve a Nash equilibrium and to create technology. So that's the question. How do you create something that is balanced in its update between left and right, and is better at converging towards a Nash equilibrium of politics at scale without, at scale, pretty much. Yeah, but thinking about all of this, then like what I can do here is, because I know that this stuff is gonna happen, and I think maybe some people at Google probably know this as well. And that's the reason why they want to create the AI, because it is this adversarial dynamic that I was talking about. But that's the problem, because the part that updates the AI in order to combat the self-fulfilling prophecy nature is done by humans. And then humans are not going to understand they're not going to be able to approach the singularity point, because we all have biases, and the nature of our intelligence is collective by itself. So that's the question. How do you compute the diversity of thinking and the essence of the multifactorial structure of the collective consciousness into an algorithm, to an AI algorithm, in order to allow the best balance of the gradient of distribution from what's considered to be unique and authentic to what's considered to be spam. So what I'm gonna do here, based on that, all of that, is I'm gonna try to reach breadth of content through using ChatGPT, and I'm not gonna modify the text. I'm just gonna fact check and see if everything is correct. And then once I have a bunch of different posts, what I'm gonna do, because that's gonna create, because the more posts you have, it's just like YouTube, it creates gravitational force. So the more higher quality posts you have, you're creating gravitational force into the system you're building, which is a funnel. And all you need from that point is to have a couple of outliers, let's say, that are able to rank on Google, and then through that is going to increase a lot the people that visit the site, because they're going to come from that article. And obviously it's very hard to predict because it's a multifractal pattern. So it's kind of like trying to predict the stock market. You're not going to be able to do it very well, because it's very hard to use past data to predict the future, and I think it's the same with creating content. It's very hard to predict which content is going to be. You can only increase the odds that the content is going to be ranked, and because of that, I think it's better to create all of these articles as a means of creating a gravitational force through the website, so that and then once I have a good base of articles on all the categories, then I can merge the articles with my unique perspective and create an article that solves a unique niche problem based on the synthesis of all the articles created with AI. And that's going to give me the edge to rank on those articles. But then because I have all these other articles, it increases the probability that people are going to stay on the site, and that is going to increase the authority. And if obviously I have to be careful and make sure I'm increasing the probability that the articles are going to have a high degree of truth to the best that I can. Because, yeah. But the only thing that I don't know about this is that how is Google going to perceive this? Because even if they rank you based on the whole structure of your website and not only which they might do because they are concerned with spam, then this becomes a very difficult problem, because then I don't know what to do exactly, because it's going to become the challenge of how to change a content that existed for a long time into something that is like, there's only so many ways you can write this algorithm, for example. So how do you determine what's copyright, what's unique or not? That's the point that is very confusing to me. I don't know what to do about it. Yeah, but this is what I'm gonna do for these boring topics. I'm just gonna, and then for stuff like blockchain or consensus mechanisms and philosophy and things like that, then I can synthesize everything and write the article on my own. And then I can use the structure that I learned from ChatGPT in order to increase my intuition over the best way to write to increase the SEO. Because the structure is obviously based on a bunch of data of what increases SEO, the titles and the way that the flow of the article, let's say. And by reading a bunch of them, I think I'm gonna naturally understand. And then I can integrate that with my own, when it gets time to write my own articles.
The process of exploring neighboring nodes and updating distances is repeated until all nodes have been visited or the destination node is reached. One of the key features of Dijkstra's algorithm is that it uses a relaxation process to update the distances of nodes. This process involves comparing the current distance of a node to the distance of the node plus the weight of the edge connecting it to the previously visited node. If the new distance is shorter, the distance is updated to the new value. Applications of Dijkstra's algorithm. Dijkstra's algorithm has many practical applications in a variety of fields. Some of the most common applications include computer science. Dijkstra's algorithm is widely used in computer science for solving a variety of problems, such as finding the shortest path in a graph, scheduling tasks, and solving mazes. Transportation engineering. The algorithm is used in transportation engineering.
So this is a part that I'm going to do some research to see if it is correct. Mapping, social networks, cell phone, Pironi. I'm just gonna look at a couple of websites, see roughly what they say. I think intuitively it makes sense, and I think it's correct. What is Amaze? I think is I think I know the name in Portuguese, but not in English. Yeah, yeah. Scheduling tasks, transportation. I think this is all correct, to be honest. It just makes sense. Like, why would you use a graph or shortest path on the graph?
Operations research. Dijkstra's algorithm is used in operations research to solve a variety of optimization problems, such as the traveling salesman problem and the shortest path problem in a network. Python naive/simple.
I think the other articles are the ones that I'm gonna have to
Operations
spend more
research.
time,
Dijkstra's algorithm.
because I don't know them. These ones are already studied, I think, 2 or 3 times already. blah, blah, blah. Yeah. This already revealed, I know that is correct, so.
In this example, the heap.heap_push function is used to insert an element into a priority queue, heap, in Python. A heap is a specific kind of data structure that maintains the heap property, which states that the parent of any element in the heap should be less than or equal to its children. Heap.heap_push, heap, item, adds the given item to the heap represented by the list heap. The function internally rearranges the elements of the heap to maintain the heap property after the insertion. The time complexity of this operation is O, log n, where n is the number of elements in the heap. Conclusion. Dijkstra's algorithm is a powerful tool for solving the single source shortest path problem in a graph with non-negative edge weights. It is widely used.
I think I'm gonna do another folder as well and do an article about heap because it is very common on all these algorithms. And I know roughly, I know what it is, but I don't know in depth of the nuances of how it works, like on the source code. So the next one, Springs. Also bought a domain name. It's vmscode.com. Luckily, I was able to get a .com extension.
Prim's algorithm. Introduction to Prim's algorithm. Prim's algorithm is a widely used method for finding the minimum spanning tree, MST, of a weighted, connected graph. Developed by Robert Prim in the late 1950s, the algorithm has become an
So this is wrong according to Wikipedia. Like this is the stuff that I was talking about before about the whole issue of truth and lies. Because even Wikipedia can be incorrect, and obviously everyone can be incorrect at any moment in time. There's no way to prove that science is the ultimate truth, and it actually is more likely that it isn't, I think, because of the Gödel incompleteness theorem. But if you think about it, it just makes sense because science is a byproduct of your whole perspective of the illusion of cause and effect relationships that creates the present moment. So there's no way to know, and then the issue is that you get into this other point that you start getting into the space where everyone says that there is no truth, and then like is the whole gender problem of what is a woman, and that's the other side of the distribution of the gradient of this computational system, that is the frequency of change between left and right that creates the mechanism of computation of the collective consciousness. But the problem with that notion is that then you can't do anything, because if you think that there are no truths, then you can't act, because how are you going to decide which way to act? It becomes an impossible problem. So you're forced into the position that you have to assign probabilities of what's true or not based on your current paradigm of thinking. So I think that the optimal approach is probably the paradoxical point that encapsulates both sides of the view, which is that you create a probabilistic structure based on what you consider to be a fact, but then you're always aware that the facts that you perceive are just density structures in space-time, because your perception of them is the computation of your awareness in relationship to the structure of space-time, which is the distribution of density in relationship to that awareness, which creates computation and creates our perception. So here, for example, who do I trust? ChatGPT or Wikipedia? I think the obvious answer for most people would be Wikipedia because it's more reliable, but that comes because of the subconscious effect of the structure of authorities in the social structure. That you create all these assumptions based on whatever is put into your brain over who should have authority for what. So if someone is dressed like a cop, for example, you're more likely to follow the instructions that they say, even though they might not be a cop, even if they are unarmed or they are weaker than you, because it's obviously the construct of your mind based on the abstraction of the collective consciousness of who should have the authority to say certain things. But then obviously people exploit that, and that's the whole problem with figuring out the truth in all these areas. There is high noise to signal, because politics is one of them, because then it gets to the whole narrative warfare and the misinformation, and the point is to confuse you and not to allow you to know what is correct or not, because then you have to rely on authoritative figures, and then the authoritative figures can make your mind. So for example, this would be like Wikipedia. Trusting what Wikipedia has to say over ChatGPT could be a bias towards what's considered to be the highest form of truth, because they manipulate your brain into thinking that. And when I say they, I just mean the system. Like I don't think there's anyone doing that. I think that because I don't view human beings as the single unit. I think everything in the universe is a part of everything else. So, and it's hard to say what's the moment where it becomes centralized or decentralized, because it's always relative. So there's no actual human being. I think it's just a collective of systems that are integrated and that creates these outputs. Yeah, so this is the second thing. Look, I think I'm gonna change this there. Let's see where is that?
Developed by Robert Prim in the late.
That's the very beginning. My biggest issue of changing the text like this is that I have to change all the lines now. It's not that big of a deal, I think. Green's algorithm is a widely used method for finding the minimum spanning tree of a weighted connected graph. The algorithm was developed by a Czech mathematician. They were rediscovered and republished by computer scientists. Robert C. Prim in 57 and this guy in 59. And it has become an essential tool in computer science. In engineering, applications in fields such as networking, blah blah blah. Yeah, obviously, it could still be wrong, but I think that highest probability is probably this one instead of ChatGPT. So, but I could be wrong about that. And that's why I think that the best way to learn things or to think about things is by trying as much as possible to reduce into fundamental principles. Because that way you increase the signal to noise ratio again. Because it's very hard to lie about fundamental principles because there is a higher density of information based on whatever my experience of reality is now, obviously, because of the whole thing that I talked about, metaphysics. But it seems to be that way now, where it's harder to lie about the laws of physics, for example, than it is to lie about who stole money from what or who started the war in Ukraine or things like that. So instead of thinking about that or focusing on that, I prefer to focus on what makes up the abstraction of human beings, what makes up the body, because that way, the more you understand the fundamental principles, you can derive the circumstances based on that. And I think that probably what we should do with machine learning models is something similar. That's why I was thinking about creating a blockchain, a network of artificial intelligence agents in the blockchain playing poker against each other over rule space of things that approximate as much as possible the fundamental principles of science, because that way you increase the probability of the density structure of density infrastructure of the geometry of the algorithm of mapping the whatever is accurate at the moment, increasing the signal to noise ratio. And I think in a way that's all that you can do through knowledge is a funnel of information, I think. So this whole process I described is probably the best you can do in an algorithm, and that's probably what they should do with artificial intelligence, I think. Because if you think about it, what a first principle really is just a higher density structure of knowledge. It's like a pyramid. So the base layer of knowledge is the fundamental principle, which in everyone's case is always going to be your direct experience, because you're directly aware of it. So it means that it has the highest probability of being reliable. And then through that, and that's why I think I tweeted about this as well some time ago, which is that I think that's the structure of reality, which is this funnel from space-time to imagination, where the highest density, the lowest density is imagination, and that's why it's unreliable, because it fluctuates too much, it's too volatile. And then the lowest layer is space-time, which is your direct experience, but your direct experience is actually the flow between the two, which creates the hologram that is your identity. That is the parsing of infinity that creates the structure of space-time. And that converges towards infinity always. So that's why entropy always increasing. It's always increasing because it's relativistic. But that process of learning the truth, I think, is this process of the funnel of from the highest or the lowest degree of density, or the lowest degree of density that has more volatility, into the highest degree, which is the fundamental principle, what we call fundamental principle, which seems to be something that that stays the same across a very big span of time. That's what a fundamental principle is, and that's what the laws of physics are. So I think that's the best you can do to increase how accurate something is. It's always going to be relative. But that's why you need multiple different agents, I think, because then it allows you to cover a greater degree of surface in space-time, because all the data is directly correlated with the structure of space-time. So the nature of the model has to increase in space-time in order to capture all the volatility of the data that exists in space-time, because that's going to make up the funnel of information that is going to increase the probability that that funnel is accurate. And then actually what you can change as well is the degree from which you go from first principle, from higher level or lower level density to first principle. And I think that depends on the complexity, which is the nuance of the situation. So the more nuance the situation has, the more variables it has, the greater the degree of difficulty to compute. And that's why it becomes a lot more difficult to know. And that's what happens with things like COVID, for example. Because there's so much complexity, then it becomes really hard. And then people exploit on the nuance and the unknown, because you can't compute. So when you can't compute, you rely on the infrastructure of authority. And that's the algorithm that people use, or that social structures use to update the knowledge of the unknown, let's say. But we know that that's hackable and is not sustainable, I think. That's the problem. So there needs to be an AI version of that, I think. It's the only way to keep up with the innovation cycles, I think, and to regulate. Also, I did a simple one of these, but I need to search on how to do this later. But I'm gonna leave this for later because the priority is to put the articles out there. I can't afford to just focus on this stuff right now. But obviously I want, yeah. I did a simple solution for now, the simplest I can find. But later on I'm gonna look into this more. I think I'm just gonna move on. I trust that this information is probably correct. Continue.
Developed by Robert Prim in the late 1950s, the algorithm has become an essential tool in computer science and engineering, with applications in
Actually,
fields
I
such
need
as network.
to reload this stuff. So it shows the new thing.
Prim's algorithm. The algorithm was developed in 1930 by Czech mathematician Wojciech Jarnik and later rediscovered and republished by computer scientists Robert C. Prim in 1957 and Edsger W. Dijkstra in 1959 and it has become an essential tool in computer science and engineering, with applications in fields such as networking, transportation, and telecommunications. In this article, we will discuss the basic principles of Prim's algorithm, its implementation and complexity, and some of its key applications. By the end of this article, readers will have a strong understanding of Prim's algorithm and its potential to solve real-world problems. Understanding the minimum spanning tree. Before diving into Prim's algorithm, it is important to understand what a minimum spanning tree is and why it is useful. A spanning tree of a graph is a tree that includes all the vertices of the graph, with a minimum number of edges. The weight of a spanning tree is the sum of the weights of its edges. A minimum spanning tree, MST, is a spanning tree with the minimum possible weight. Finding the MST of a graph can be useful in a variety of situations. For example, in telecommunications, the MST can be used to find the most cost-effective way to connect a set of cities with telephone lines. In transportation, the MST can be used to find the most efficient route for a trucking company to take between a set of cities. In networking, the MST can be used to find the most reliable way to connect a set of computers in a network. Understanding Prim's algorithm. Prim's algorithm is a greedy algorithm that is used to find the MST of a weighted, connected graph. The algorithm starts with an arbitrary vertex, and at each step, it adds the next closest vertex to the current tree. The algorithm continues until all vertices have been included in the tree. The basic steps of Prim's algorithm are as follows. Start with an arbitrary vertex as the first vertex of the tree. Add the vertex with the smallest weight that is connected to the current tree to the tree. Repeat step 2 until all vertices have been included in the tree. One of the key features of Prim's algorithm is that it is a greedy algorithm. This means that it makes locally optimal choices at each step, without considering the global consequences. While this can sometimes lead to suboptimal solutions, it also makes the algorithm relatively simple to implement and
Let me
understand.
check that. I think it is, but let me double check. Yeah. Rebecca.
While this can sometimes lead to suboptimal solutions, it also makes the algorithm relatively simple to implement and understand. Implementing Prim's algorithm. There are several ways to implement Prim's algorithm, including the lazy and eager approaches. The lazy approach is more efficient for dense graphs, while the eager approach is more efficient for sparse graphs. The lazy approach involves maintaining a priority queue of the vertices that are not yet in the tree. At each step, the vertex with the smallest weight is removed from the queue and added to the tree. The eager approach involves maintaining a priority queue of the edges that connect the tree to the vertices that are not yet in the tree. At each step, the edge with the smallest weight is removed from the queue, and the vertex at the other end of the edge is added to the tree. Time and space complexity. The time complexity of Prim's algorithm is O, E log V, where E is the number of edges and V is the number of vertices in the graph. This makes the algorithm relatively efficient for both dense and sparse graphs.
Yeah, I think that this information is correct. I'm just gonna continue. I'm gonna continue on this one, and I think maybe one or two more. I think I stopped off stream. I did a couple of them off stream, and I stopped on the A-star algorithm. And that one is really hard. So I think I'm gonna on the break I'm gonna eat something and watch videos about A-star. So understand more how it works.
This makes the algorithm relatively efficient for both dense and sparse graphs. The space complexity of Prim's algorithm is O, V, as the algorithm only needs to store the vertices and edges in the current tree. This means that the algorithm does not require a significant amount of memory, even for large graphs. Applications of Prim's algorithm. Prim's algorithm has a wide range of applications in computer science and engineering. Some of the most notable applications include network design. Prim's algorithm can be used to find the most cost-effective way to connect a set of computers in a network. This is known as the Steiner tree problem, and it is often used in telecommunications and networking.
Let's see this again.
This is known as the Steiner tree problem.
Steiner tree problem. I should leave one tab open here for this. Just gonna put them here. Oh, actually, I had one there. Okay, whatever.
Steiner tree problem. Python naive / simple implementation. Import heap def prim graph start hashtag initialize mst and priority queue mst equals set priority queue equals 0 start heap.heapify priority queue while priority queue hashtag get edge with
Okay. Now let's look at the algorithm. I already took a look at this. I think it's correct here. So I'm just gonna continue. I'm pretty sure it's correct. I spent a bunch of time thinking about this, so.
This function takes in a graph represented as an adjacency list in a starting vertex, and returns a set containing the vertices of the MST. The heap library is used to implement a priority queue, where the priority is the weight of the edge. The algorithm starts by initializing an empty MST and adding the starting vertex to it, and adding all edges adjacent to the starting vertex to the priority queue. The while loop continues until the priority queue is empty. In each iteration, the edge with the smallest weight is extracted from the priority queue, and the vertices of the edge are added to the MST if they are not already in the MST. Then, all edges adjacent to the new vertex are added to the priority queue. Conclusion. Prim's algorithm is a powerful and widely used method for finding the minimum spanning tree of a weighted, connected graph. With its simple implementation in efficient time and space complexity, the algorithm has become an essential tool in computer science and engineering. Whether you are working in telecommunications, transportation, or data mining.
Let's go to the next. Cruise calls. Until the A star, I'm gonna go really fast because I already look at these ones. I'm just reviewing them again to make sure that I get the details, or if there's anything that might be wrong, any facts that I didn't check. But then on the A star, I'm gonna take more, this one, I'm gonna take more time to understand them. Yeah, so cruise calls. I mean, the worst case scenario, I'm gonna have learned a lot about everything, so I still think it's a win, regardless of what happens.
Kruskal's algorithm. A comprehensive guide to understanding and implementing the algorithm. Kruskal's algorithm is a popular algorithm for finding the minimum spanning tree, MST, of a graph. It is a greedy algorithm that is used to find the optimal solution for a wide range of problems, including network design, image segmentation, and cluster analysis. In this article, we will delve deep into the workings of Kruskal's algorithm, its implementation, and its various applications. Understanding Kruskal's algorithm. The minimum spanning tree of a graph is a tree that spans all the vertices of the graph and has the minimum possible total edge weight. Kruskal's algorithm is used to find the minimum spanning tree of a graph by iteratively selecting the edges with the lowest weight and adding them to the tree until all the vertices are spanned. The algorithm starts by sorting the edges of the graph in increasing order of their weight. Then, it iterates through the edges, adding each edge to the tree if it does not form a cycle. If the edge forms a cycle, the edge is discarded, and the next edge is considered. This process continues until all the vertices are spanned, and the tree is complete. Pseudocode for Kruskal's algorithm. Kruskal, G, sort the edges of G in increasing order of their weight T equals for each edge, U, V, in G if T plus, U, V, does not form a cycle add, U, V, to T return T. Implementing Kruskal's algorithm. Kruskal's algorithm can be implemented using various data structures, including arrays, lists.
Yeah, this one I spent a bunch of time because I didn't know how the disjoint set data structure worked and how the union worked, but I'm pretty confident now that this is the correct solution and I understand how it works. Not sure if I would be able to apply it in a problem if I didn't know that the problem required this, but I think I understand how it works. It divides everything into sets, and then through the iterations, it connects them into the same set. And if it has a cycle, it detects the cycle.
Here, graph is a dictionary containing the following fields. Num-vertices, the number of vertices in the graph. Edges, a list of edges in the form U, V, W, where U and V are the vertices connected by the edge and W is the weight of the edge. The find and union functions are used to implement a union find data structure, which is used to keep track of which vertices are connected to each other in the minimum spanning tree. In this example, the graph is sorted by the weight of edges in the first line and the parents is a list that is used to map the nodes to their respective sets. They start with each having its own set, but then the union function is applied to merge the sets if the parent of the nodes are different. The find and union function combined make sure there are no cycles, returning in the end the minimum spanning tree. Applications of Kruskal's algorithm. Kruskal's algorithm has a wide range of applications, some of which include network design. Kruskal's algorithm can be used to find the optimal solution for designing a network, such as a computer network or a telecommunications network. The algorithm can be used to find the minimum spanning tree of the network, which can then be used to determine the optimal configuration of the network. Image segmentation. Kruskal's algorithm can be used in image processing to segment an image into multiple regions. The algorithm can be used to find the minimum spanning tree of the image, which can then be used to segment the image into multiple regions. Cluster analysis. Kruskal's algorithm can be used in cluster analysis to find the optimal solution for grouping similar data points together. The algorithm can be used to find the minimum spanning tree of the data points, which can then be used to determine the optimal grouping of the data points. Conclusion. Kruskal's algorithm is a powerful and versatile algorithm for finding the minimum spanning tree of a graph. It is used to find the optimal solution for a wide range of problems, including network design, image segmentation, and cluster analysis. With this article, you should have a solid understanding of the workings of Kruskal's algorithm, its implementation, and its various applications.
I think it's very likely that it is correct, but the only thing that I still don't understand really well is how it prevents from having cycles. And I think I spent a lot of time thinking about this before, and I kind of get it, but it's still weird to me on how it works here. So I'm not 100% sure about that. I understand how the union works, It starts off everyone on their own set, and then if the parents are different, it merges the set. And I think is this merging of the sets that prevents the cycle, but I don't understand really well in the code how it works. Like where is the point that it stops the code because of the cycle? I think it is because of the edge, I think. Yeah, because the node is gonna be the same. The parent is gonna be the same, I think. Eventually, if it has a cycle. I think that's how. Yeah, but then, because it doesn't stop the... I think it doesn't prevent the graph to have a cycle. It just prevents the minimum spanning tree of the graph to have to map to a cycle, I think. That's what happens. Because I don't see how it would stop. I think if the parents are the same, then it is a cycle. I think. Yeah, that's the point. So it merges everything because the parents are different until it gets to one set. But if the parents are the same, then it's not gonna go through the edge. So that's why it doesn't, and then it doesn't append to the minimum spanning tree and doesn't call union. But it doesn't break the code if it has a cycle. I think that's the only point of confusion that I still have. Maybe I'll watch one more video about this, but the videos I don't learn really well from them because they're not uh, for my style of learning. So I have a hard time learning from the videos that are available about these algorithms. Like, they don't explain things that in a way that it makes it easier for me to understand. Like they explain because the concept I think I have an easier time understanding the concept, and I think that's what they spend the most time talking about. Most of them, the videos. But then the actual code in the implementation of the concept is that's where I get lost a little bit, depending on the algorithm. I'm gonna watch this show about Cruskos and the other ones about A-Star while I eat something, and then I'm gonna continue to review the graphs. So I'll be right back.
Hello and welcome everyone. This is a short tutorial on solving for the minimum spanning tree of a weighted graph using Kruskal's algorithm. Let's begin with the weighted graph data structure. We know that a graph consists of a set of vertices, such as the circles that I'm drawing here, and a set of edges, which connects pairs of vertices. Recall that this graph is weighted, so we must also assign integer-valued weights to each edge. We're at 6, 1, 5, 5, 5, 3, 6, 4, 2, 6. And this is the weighted graph that we will reference throughout the rest of this tutorial. Next, we define a spanning tree. A spanning tree is simply an unrooted tree that spans the same vertex set as its referenced graph. Here's an example. We begin by drawing the vertex set of our original weighted graph. Then we select edges from our reference graph such that we generate a tree. So here is one particular set of edges that generates a tree. And notice that we pull all of these edges from our referenced weighted graph. This is a spanning tree. However, a graph may have multiple spanning trees. Here's another. Draw the same vertex set, of course. And let's say we select these particular edges with the corresponding weights. Since there are potentially many spanning trees, we would like to find the minimum among them. The minimum spanning tree should minimize over the sum of the edge weights. As an example, consider the first spanning tree that we've drawn. The sum of the edge weights is 19. And for our second spanning tree, the sum of these edge weights is 21. In Kruskal's algorithm is a procedure to solve for the minimum spanning tree of a weighted graph. So let's begin this procedure by drawing the original vertex set. And now the algorithm begins by selecting the lowest weighted edge, which in this case is 1. And for each edge selected, we accept it if it does not create a cycle, where a cycle may look something like this, or perhaps even longer like this. These are cycles. Cycles are bad. We don't want cycles. Then we proceed with the next lowest weighted edge and ask if it creates a cycle. If it does not, we accept it, such as this 2 here. We continue. Take 3, it does not create a cycle, therefore we keep it. Take 4, it does not create a cycle, therefore we keep it. And now let's try selecting one of these 5s here. Well, this 5 here creates a cycle, so we shouldn't keep it. Go ahead and remove this. And now, can we take this 5? This 5 also takes, or creates a cycle, so therefore we cannot keep it either. However, we can take this 5. And now, note that when all vertices are connected, you're done. So the sum of these edge weights is actually 15. This is how you can solve for the minimum spanning.
Okay, I'd like to talk about Kruskal's algorithm today, and I want to tell you when I first heard of it. I was an undergraduate and I had a summer job, and I was supposed to, or I needed to learn some graph theory for the job. So I got a book out on graph theory. I'm going through learning this stuff, and all of a sudden this page pops out at me and says Kruskal's algorithm, and I'd never ever heard of it. So I was surprised, but I learned what it was, and I never again saw it while I was an undergraduate. It wasn't until I was in graduate school when we had a real course in algorithms that I once again saw it and realized how important the algorithm is in computer science. The reason, of course, that it wasn't covered so much as an undergraduate is that it was in the early days of computer science. I was actually at my school the first year that they actually had a major in computer science, and the curriculum was not as developed as it is now. We didn't really have a course in algorithms. There were some algorithms covered as part of other courses, but there was no course in algorithms per se. Okay, so now I would like to talk about how Kruskal's algorithm works. Okay, imagine we have some villages, and there's no roads connecting villages, and we would like to build a network of roads connecting the villages together. And there's a cost for putting a road between each pair of villages. So, for example, in this graph, the black ones are nodes, but they represent the villages. And between each pair of villages, there's a cost. For example, between these 2 villages, the cost is 30 to build a road. Between the relatively cheap road, between these 2 villages, the cost is 90. That's a very expensive road. And we actually have some villages that we can't even build a road between. You might think that's a really, really expensive road. So we can't build a road between these 2 villages. And so what we'd like to do is find the cheapest road network that would connect all the villages together. And that's a minimum spanning tree. So given that graph that we just looked at, the blue edges are the minimum spanning trees. So notice that they form a tree, and this is the cheapest tree that you can get from those original edges. And you can check it yourself, but there it is. Okay, so here's how the algorithm works. We're going to go through the edges, or the roads, from cheapest to most expensive, and we're going to put them into the minimum spanning tree. And we will not put a road in if it creates a cycle in the graph, because a cycle is basically a redundant road network. You don't need all of the roads in a cycle to get rid of one, and you can still get everywhere in the network. So in this example, the cheapest road is the 10 road, and so what we'll do is we're going to put that into the minimum spanning tree. So we're going to erase the road there, and we're going to draw a blue edge to represent an edge in the minimum spanning tree. Then we're going to go to the next cheapest edge, and that's the 20, which is down here, and we will put that road into the minimum spanning tree. So we'll erase the black edge as a potential road, and we're going to put it in blue as an actual road in the road network for the village. Then the third cheapest edge is the 30, and so we will erase that edge and put it into the minimum spanning tree. The next cheapest edge is the 40, and that's over here, so we will erase that edge and put it into the minimum spanning tree. The next cheapest edge is the 50, so we erase the edge from the 50, and notice that creates a cycle, and so we don't put that into the minimum spanning tree, it would just be a redundant edge. The next cheapest edge is the 60, so we'll erase that edge, and we will put it into the minimum spanning tree. The next cheapest edge is the 70, so we will erase that edge and put it into the minimum spanning tree. The next cheapest edge is the 80, we will erase that edge, but notice again that creates a cycle like this, so we're not going to put it into the minimum spanning tree. And finally, the last edge is the 90, so we'll erase that edge, but that edge also creates a cycle, and so we will not put that into the minimum spanning tree. And the blue edges that are left here are the minimum spanning tree for this graph. Okay, to finish up, I just want to tell you how my uncle came to this algorithm. When he was a graduate student, there was a paper being passed around, probably tattered, because this was the days before copy machines, so you couldn't really copy things. And he got hold of this paper, and he found it difficult to follow what was being said in the paper, so he thought that he should try to really understand it and write it up for himself what was going on. And once he understood what was happening, he was able to discover what we now call Kruskal's algorithm, and he wrote just notes for himself. A friend of his encouraged him to publish this as a paper, and he did so, and it turns out that was very lucky for him, because now it's become known as Kruskal's algorithm, and the rest is history. Into the minimum spanning tree. And said in the paper, so he thought that he should try to really understand it and write it up for himself what was going on. And once he understood what was happening, he was able to discover what we now call Kruskal's algorithm, and he wrote just notes for himself. A friend of his encouraged him to publish
Welcome to this video on pathfinding. So in this first episode we're going to be taking a look at how the A-star algorithm actually works, so that once we begin programming it in the future episodes, you've got a pretty good understanding of why it works and where we're going. Alright, so here we have a grid of nodes, the white nodes representing the walkable areas in our map, and the black nodes representing the obstacles. So of course we're trying to find the shortest path from node A to node B, and what we need to do first is decide how far apart the nodes are. So it would be quite natural to say that the distance between two nodes is 1, and therefore by Pythagoras the distance diagonally is going to be the square root of 2, which is approximately 1.4. So quite a common practice is just to multiply those two numbers by 10, and to use the nice integer values of 10 across and vertically, and 14 for the diagonals. Alright, so I've removed the obstacles for a moment so we can see how the algorithm's going to run when there aren't any obstructions. So the algorithm begins by going to the starting node, node A over here, and looking at all of its surrounding nodes and calculating some values for each of them. So the values in the top left corner of each node are called the node's g-cost, and that is quite simply how far away that node is from the starting node. So this node in the top left corner has got a g-cost of 14, since it's just one diagonal move away from node A. In the top right corner of each node is the node's h-cost, which is basically the opposite of g-cost, is how far away the node is from the end node. So this node is 2 diagonal moves away from the end node, so it's got a h-cost of 28. Now the big number is the node's f-cost, and that is very simply g-cost plus h-cost. So now the algorithm is going to look at all of these nodes, and it's going to choose the one with the lowest f-cost to look at first, and that is of course this 42 in the top left corner. So it will mark this now as closed, so it will appear red, and it will then calculate all of these values again for all of its surrounding nodes. And it's quite simple to see what's happening here. These f-costs are just staying the same as it moves towards the target, because the g-costs, the movement costs, are increasing, and the h-costs are decreasing, and they're just sort of balancing each other out. So it basically explores the path straight to the end. Well, no point having pathfinding in your game if you're not going to have any obstacles, so let's add those back in and run through the algorithm once more and see what happens. So once again, we look at all the surrounding nodes and calculate their f-costs, and we'll go with this lowest f-cost of 42, and now we have a scenario where we have 3 nodes, each with an equal f-cost of 48, and so what we'll do to sort of decide which one to pick is we'll look at which one is closest to the end node, in other words, which one has the lowest h-cost. This has an h-cost of 38, this is also 38, and this one's 24, so we'll go with this one. Now, as you can see, the f-costs are increasing each time, since we're not going in a straight line towards the end, so even though the h-costs are decreasing by a little bit each time, the g-costs are increasing by even more, resulting in a more expensive path. So now the two nodes with the lowest f-cost on the map are these two 48s over here. They've got the same h-cost, so we can pretty much choose one at random. Let's go for this one over here. And now we have to look at the other one. And at this point, the most sort of promising node, as it was, is 54 over here, and we explore that. So now we'll look at this other node with an f-cost of 54, but one thing I'd like to draw your attention to quickly is the node just to the left of it with an f-cost of 68. If we look at its g-cost, it is currently 38, but if we look how far away it is actually from node A, it's just 10, 20, 30 away. So obviously this has come on a path something like diagonally up here, 14, then across for 24, and then down diagonally to make 38. So as we explore this 54 over here, and explore all of its surrounding nodes, you'll see how the 68 updates to reflect the new best path to this node. So it now has an f-cost of 60, and it is the most promising node on the map, so we'll explore that. And now we have a bunch of 62s to look at. Not much to say in the way of commentary here, just exploring all of these lowest f-costs, until now we can come back to the 68, and we explore that, and we get to explore the other 68, and now we'll observe the same effect that we saw in the first example, where we'll just go straight line to the end node, and the g-costs and the h-costs will balance each other out, and the f-costs won't change, and we'll just go straight to the end. So hopefully you can see how this is guaranteed to find the shortest path, since as soon as you're not moving in a straight line towards the end, the f-costs are going to increase, and then it will start looking at the other potential options. Let's look at one final example. In this case, I have hidden the g-costs and the h-costs, and I'm instead showing these little arrows which are basically indicating where these nodes have come from. So when we explore the 58 over here, you can see all of its surrounding nodes are now pointing to reflect that they sort of originated from this node. Of course, the 64 and the 58 over here, even though they are, its neighbors have not updated to show that they're coming from this node, since it should be a worse path. In other words, it would have a higher f-cost if we were to get to, say, this node over here, by going diagonally up and then down. So it will only update if it is in fact a better path that's being offered. So we continue by looking at this 58, and that yields a 66, so we go back to the 58 at the beginning. And now once again, just to demonstrate this, you can see the 66 is coming on the sort of slower diagonal path, so it'll be much quicker to just go horizontally across. So as we explore this 58 and look at all its surrounding nodes, that node is going to update to reflect that. And as you can imagine, we just go straight to the end now. So the point of these arrows, of course, is just that now that we've reached the end node, we can sort of retrace our steps and find the path that we took to get there. Alright, so while that is still hopefully fresh in your mind, let us look at how this would work in terms of the actual programming. And so what I've got here is just a bit of pseudocode, meaning that it's not in any particular language, it's just basically a set of instructions. Alright, so to start off with, we create two lists. The first is called the open list, and this list is for storing all of the nodes for which we've already calculated the f-cost. So in the diagrams I've been showing all the nodes that were colored green were the ones that were currently in the open list. Then the closed list is basically a set of nodes that have already been evaluated. So those are all of the ones that I sort of ticked off as red in the diagrams once we'd looked at all of their neighbors. So once we've created those two lists, we add the starting node to the open list, so that's currently the only thing in the open list, and there's nothing, of course, at the start in the closed list. And then we enter a loop. So inside of the loop, we create a little temporary variable called our current node, and this is equal to the node in the open list with the lowest f-cost. So at the beginning, that would of course be the starting node, since it's the only one in the open list. And we remove the current node from the open list, and we add it to the closed list. Then if the current node is the target node, then we can assume that we found the path, and we can just exit out of the loop. Otherwise, we're going to go through each of the neighboring nodes of the current node And first of all, if it's not traversable, or if it's in the closed list, then we'll just skip ahead to the next neighbor and ignore it. And if that's not the case, then we check a couple of things. So first of all, if the new path to the neighbor is shorter than the old path, so say for example that the neighbor is already in the open list, as we've seen in some of the diagrams, but then the new path is shorter, so we have to update that node to reflect that we found a better path to it. So if that is true, or if the neighbor is not already in the open list, then we set the f cost of the neighbor, which we do obviously by first calculating the g cost and the h cost, and then we set the parent of the neighbor to the current node. So that's what I was trying to show visually with the arrows. We sort of keep a reference to where that node came from so that we can retrace the steps once we get to the end node. Then finally, if the neighbor is not in the open list, then we just add the neighbor to the open list, and we keep looping this, and eventually the current node is going to be equal to the target node, and the path will have been found. We'll exit out of the loop, and we'll just run a quick little method to look at all of the parents going back from the end node until we find the starting node, and that will be our path. Alright, so that's pretty much all there is to it. Of course, as we begin actually programming this in C# in the future episodes, we'll look at a couple of things a bit more in-depth, but for now that should hopefully give you a pretty good understanding of how A* works, and if you're unsure about anything, don't hesitate to leave a comment and I'll try to help you out. Otherwise, I've also linked a couple of really good articles in the description, which you could have a look at as well. Alright, so thank you very much for watching. Cheers.
Imagine that you're a mouse in a maze. You want to find the shortest path to the piece of cheese at the end of the maze in the fastest way possible. Well, you could search the entire maze exhaustively to find the cheese, but this would take way too long. Let's say that now you can smell the cheese. This is called a heuristic. The mouse kind of has an idea of which way to go towards the cheese. Sometimes the mouse goes off course, but it won't go too far off before realizing it's a mistake. You can model this maze as a graph, and the sense of smell as a heuristic. As the mouse gets closer to the cheese, the smell gets stronger. At the beginning of the maze, the heuristic or smell indicates that the cheese will be closer if the mouse goes right, so the mouse will go that way. So the heuristic is allowing us to prioritize our options when multiple are presented to us, and it's giving us a rough estimate or an idea of how far we are from the goal. So if we prioritize the distance from the start state plus our heuristic, this gives us an estimate of the total path length, and our goal would be to minimize this total path length. Let's do an example. First, we add some distances to our graph. This represents how far the nodes are from each other. Let's also add some heuristics. So we'll put the red starting node on our queue and give it a priority of 0 plus the heuristic value, which is the estimated distance to the cheese. We then pop this node off the queue and add on its children. Taking a look at the queue, we see that the node with a purple heuristic of 85 has the lowest priority value. The priority of 88 means that the estimated distance from the start node through this node to the cheese is 88. Since this is the lowest priority on the queue, we take the path along this node. So we pop it off and add its children. If we continue going this way, we'll search these parts of the graph shown in blue. This is way better than an exhaustive search like BFS. So again, a heuristic is like a sense, a hunch, or another way to perceive the world. The A* algorithm harnesses the power of good heuristics to search less area and find your goal faster.
Imagine that you have a set of tasks of different importance, and you want to store them in a way that will always let you quick access to the most important one. If you just throw them in an array, every time you want to find the most important task, you'd need to traverse the whole array to find it. An operation holds time complexities of n, kinda slow. But what if you put them in an array sorted by importance this time? It's true that the most important task will always be on the last cell, which costs O of 1 to extract, but you'd have two new problems. Building the array would cost you O of n log n because you have to sort it, and inserting an element would cost you O of n because you need to respect the order, so you have to insert it in a specific place. And even if you use binary search, you'd still need to maybe shift elements, which causes O of n time complexity. What's the solution then? Well, we have this data structure that you will learn about today that is called the heap. The heap is a tree data structure where each node is smaller than or equal to its children if it's a min heap, or greater than or equal to its children if it's a max heap, depending on the type. For example, the one on the screen is a min heap. And because the root is smaller than or equal to its children in case of min heap, and its children are also smaller than or equal to their children, and so on, then the root is smaller than or equal to all the nodes in the heap. Hence, the root is always the smallest element. Same logic for max heap, but with the word greater. We deduce that getting the smallest or greatest element in a min heap or max heap respectively costs O of 1, because we know that is the root. It's a great advantage. We have different variants of the heap. We have the binary heap, the Fibonacci heap, the 2-3 heap, and many other ones. Today, we'll study the most famous one, the binary heap. The binary heap is a complete binary tree that respects the heap property. A complete binary tree is basically a binary tree where every level is completely filled, except maybe the last one, but all its nodes have to be as far to the left as possible. So we can neither have a null value in a non-last level, nor a null value before a node in the last level. To store a binary tree, we usually have a tree class or something like that, but when the binary tree is complete, like for the binary heap, we can just store it in an array, which is more efficient. Why? Because when a binary tree is complete, we have no problem to find the related nodes when we store it in an array. For any node at the index i, we can find its left child, which is at the index 2 i plus 1, its right child, which is at the index 2 i plus 2, and its parent, which is at the index I minus 1 divided by 2. Therefore, we can easily move between the nodes just by calculating the index. And that's what we'll do when we implement the binary heap. We will store it in an array, but I will still show you the true representation to understand what's happening. We have 5 main operations that we need in a binary heap. We want to be able to insert an element, get the min or max element, extract the min or max element, which means getting its value but also removing it from the heap, update the value of a node, and build a heap. You need to know that we cannot add, update, or remove a node from a heap randomly. We need to respect the heap property. For example, if we have this min heap and we insert 5 without doing anything else, we would break the heap property. 10 is not smaller than or equal to its children anymore. To respect the heap property, we need to apply an operation called sift. We have 2 sift operations. We have sift up and sift down. When the node that we want to reposition is at the bottom, we apply sift up, and when it's at the top, we apply sift down. In sift up, we keep swapping the node with its parent while smaller. For example, with the 5 here, it's smaller than its parent, so we swap. It's still smaller than its parent, so we swap. It's not small anymore, so we stop. The heap property is respected again. In code, We want to sift out the element at index I, so we calculate the index of its parent as shown earlier. Then while it didn't become the root or it's smaller than its parent, we swap the node I with its parent, and I becomes parent index because it took its place in the heap. We also recalculate the parent index for the next iteration. That's it. For sift down, we keep swapping the node while it has a smaller child. If both are smaller, we swap with the smallest one. For example, if we want to sift down 7 in this heap, its right child is smaller, so we swap. Now its left child is smaller, so we swap. Now both are not smaller, so we stop. Heap property is respected again. In code, we want to sift down the element at index I. We start by calculating indexes of left and right children as shown earlier. Then while the node I is greater than one of them, we start by determining the smallest one. The smallest one is the left child if the right one doesn't exist or the left one is smaller than it, else the smallest one is the right child. Now that we found the smallest, we swap between it and the node I. We update the index I because it took the place of the smallest, and we recalculate the indexes of left and right for the next iteration. That's it. And in both of these operations, at each iteration, the node moves by one level in the heap, so the number of iterations depends on the height of the heap. And because the binary heap is a complete tree and a complete tree is always balanced, then the height is an O log n, where n is the number of elements in the heap. So the time complexity of sift up and sift down is O log n. Okay, we know how to sift up and sift down, but why do we need these operations? We need them to insert, update, and delete elements as we will see now. To insert an element in a heap, we just need to insert the value at the end of the array, but it may break the heap property, so we apply sift up on it to take it to the right place. Sift up because it starts at the bottom of the heap. And this operation has an O log n time complexity because we're calling sift up. The second operation is getmin, and we know that in a min heap, the smallest element is always at the root, which is the element at index 0 in the array, so we just return a heap of 0, if it exists obviously. We get an O of 1 time complexity for this operation because we already know the index. Next operation is extract min. Here we want to get the minimum value, but also to remove it from the heap. First of all, in a tree, we can't just delete the root directly, because its children will have no parent. What we do is that we first swap it to the leaf node, and we delete the node that was the root previously. It gets safely deleted because it's a leaf, it has no children. And in a heap, we do the same thing. To delete the root, which is the smallest element, we first swap it to the leaf, we swap it to the last element in the array, and we pop to remove the node. But this operation may break the heap property, so we apply sift down on the new root to take it to the right place. Sift down because the root is at the top. In code, we first check that the heap is not empty, then we save the value of the smallest element because we will need to return it later. Now we swap the root with the last element, and we pop to remove the node. We also save down the new root, it's at index 0, and return the main value. The time complexity is also O log n because we're calling sift down. Next operation, updating the value of a node. We actually have a structure that respects the heap property, but if we update the value, it may break the heap property, so we have to sift. To know if we should sift up or sift down the updated node, we compare the old and the new value. If the new value is smaller, then the node may need to go up, so we sift up. Else if it's greater, then the node may need to go down, so we sift down. Let me show you two examples. Let's update 7 with 2. The new value is smaller, so we sift up. 2 is smaller than its parent, 6, so we swap. It's still smaller than its parent, so we swap. Now we stop because it became the root. Second example, let's replace 12 by 16. The new value is greater, so we sift down. 16 is greater than its left child, so we swap. It has no children anymore, so we stop. The heap property is respected again. In code, it depends on if we have the index of the element that we want to update or not. If we do, we just save the old value to compare later. We update heap of I by assigning the new value, then we compare. If new is smaller than old, we sift up, else we sift down. This operation costs O log n because of sifting. But if we don't have the index, we first need to find the index of the element that we want to update. So if it exists in the heap, we search for its index, then we call the update by index function we made now. And this operation costs O of n because we first need to search for the element. So updating an element costs O log n if we have the index and O of n if we don't. And last operation, building the heap, also called heapify. The optimized way to do so is to traverse indexes of the array that we want to heapify backwards and sift down each element. It's optimized because the cost of sifting down depends on the number of levels between the node and the bottom of the heap. And because we have more nodes that are closer to the bottom, then it's better to use sift down rather than sift up. Sift up we need more operations to process the bottom nodes because they are far from top. And we traverse backwards to start from the bottom of the heap to avoid sifting down a node and having to do it again later. Let me show you an example. We have this array that represents this binary tree and we want to heapify it. We start from the end of the array. The nodes of the last level have no children, so nothing will happen. Then 7, it has no child, nothing happens. Then 14, both its children are smaller, we swap it with the smallest one. Next node, 15, same thing, we swap it with the smallest child, and it has no children anymore. Next node, same thing, we swap with the smallest one. Next node, 18, 3 and 7 are both smaller, we swap with the smallest one. 18 still has smaller children, we swap with the smallest one. Next node, 11, it has smaller children, we swap with the smallest one. It still has a smaller child, we swap. Last node, it has smaller children, we swap with the smallest one, 3. It still has smaller children, we swap. Now both its children are greater, we stop swapping. And we finished heapifying. The structure now respects the heap property. What about the time complexity? You need to know that when a tree is complete, the last level has at most around n by 2 nodes, where n is the total number of nodes. The level above has around n by 4, then n by 8, and so on until the first level that contains one node, the root. And in sift down, the maximum number of iterations is the number of levels between the level of the actual node and the last level. So nodes of the last level are already in the last level. They can't go down. Let's say that their cost is 0 because we do 0 iterations. Nodes of the level above do at most 1 iteration because they are 1 level far from the last one. Let's say that their cost is 1. Then the level above is 2 levels far from the last one. Let's say that the cost is 2. And so on until the root that may require log of n minus 1 iterations to sift down. And the total cost of heapifying is the sum of each node multiplied by its cost to sift down. We have n by 2 nodes that cost 0, n by 4 nodes that cost 1, n by 8 nodes that cost 2, and so on until 1 node that costs log of n minus 1. This sum represents the sum of k times n divided by 2 power k plus 1, where k goes from 0 to log of n minus 1. We take n divided by 4 out of the sum, so now we have n by 4 multiplied by the sum of k times 1 divided by 2 power k minus 1. Take some seconds to grasp this. The terms of this series are all positive, so this series is smaller than this one, where k continues to infinity. And it's fine to work with this one because we're searching for an upper bound. 1 divided by 2 power k minus 1 is 1 power k minus 1 divided by 2 power k minus 1, which we can replace by 1 divided by 2 power k minus 1. Now let's replace 1 divided by 2 by x, and we notice that k times x power k minus 1 is the derivative of x power k we replace. And this series, the sum of x power k where k goes from 0 to infinity, is a known series. Its value is equal to 1 divided by 1 minus x. Now we derive 1 divided by 1 minus x. We get 1 divided by 1 minus x squared. Remember that x is 1 by 2. We replace. 1 minus 1 half is 1 half, and 1 half squared is 1 divided by 4. Now we have n divided by 4 times 1 divided by 1 divided by 4, which is equal to n divided by 4 times 4, which is equal to n. We found out that the cost of heapifying with sift down is n. We get a time complexity of O of n, better than O of n log n that we would get if we use sift up. Okay, now we know what is a binary heap, its main operations, their time complexity, but where would we use it? To answer this question, let's see two applications of binary heaps, heap sort and priority queues. But before, know that here we implemented a min heap, but implementing a max heap uses the exact same logic. We just reverse the operators and change some names. You'll find the code below. Let's start with heap sort. Heap sort is a sorting algorithm that uses a heap data structure. It heapifies the array that we want to sort, then it keeps extracting min until the heap becomes empty. That's it. It's like selection sort, where we keep searching for the minimum in the unsorted part. But searching for the minimum in selection sort costs O of n, and we do it n times during the process. This is why we get an O of n squared time complexity for selection sort, which is not the case for heap sort. Remember that extracting min from a heap costs O of log n only, not O of n. This is why we'll get an O of n log n time complexity. Here is an example and what happens when applying heap sort. We know the queue data structure, a data structure that works on the first in first out principle, where an element enters from the back and goes out from the front. But in a priority queue, elements have a priority related to them, and we want that the element with the highest priority comes always in front. We can implement the structure with a linked list or an array, but one of the best implementations is by using a heap, because of the low time complexity of its main operations. So in reality, our priority queue will just be a heap, either min heap or max heap. Main operations of a priority queue are enqueue, dequeue, peek, which returns the element at front, change priority, and is empty, which says if the queue is empty. And because we're using a heap, enqueue is done just by inserting the element in the heap, dequeue is done by extracting max in case of a max heap, peek is done by returning get max in case of a max heap, change priority is done by using update, and is empty is done by just checking if the length is equal to 0. And we finished implementing the priority queue. Note that to have the index and be able to change priority and overlap n, we may need to use another structure to keep track of each element and its index in the heap. Also, note that there may exist a library for priority queue in your language to avoid reinventing the wheel. For example, in Python there is heap queue. And the priority queue has many applications. We can use it in Dijkstra's algorithm, Huffman coding algorithm, Prim's algorithm, and many other ones. We will see them in future videos, inshallah. We reached the end of this video. In this one we discovered the heap data structure, its advantages, its implementation, and some of its applications. I hope that you understood all of this. Please subscribe and share this video, and see you in the next one.
Hey everyone, welcome to another video by Simplilearn. In this video, A-star algorithm, we're going to teach you everything that you need to know about the A-star algorithm, which is a pathfinding algorithm used to find the shortest distance between 2 points. So, let's get started. Before we dive into this video, let's take a look at what you can expect to learn by the end of this video. What's in it for you? First, we're going to answer the burning question that you have in your mind. What is the A-star algorithm? Next, we're going to take a look at the basic concept behind the A-star algorithm and the mathematical function which makes it tick. Then, we'll talk about how the A-star algorithm works with the help of a case study. Then we'll take a look at the flowchart of the A-star algorithm, using which you can implement the A-star algorithm in any programming language. And finally, we'll take a look at how the A-star algorithm can be implemented with the help of Python. So, what is the A-star algorithm? Before we talk about the A-star algorithm, let's talk a bit about search algorithms. In computer science, a search algorithm is an algorithm which typically solves a search problem. They're used to retrieve information which is stored within some data structure like arrays, stacks, trees, hash buckets, etc., or calculate the search space of a problem domain, either with discrete or continuous variables. So consider you have a stack S which contains 4 elements. Now a stack is an ordered collection of items in which you can add a new item and remove an existing item at the same time. In stacks, you can put in an item on top of another item and you can't access the elements below the top element without removing the top element first. So suppose we want to find the index of say an element in the stack, say 64. So we're going to run it through a search algorithm to find 64 within our data structure. What the search algorithm is going to do is that it's going to take a look at the top element and see that it's not 64. It's going to remove the top element and move on to the next element. Again, it's going to compare and see if it's 64. If it's not, this element too will get removed and then it'll move on to the next element in the stack, which is 64. In this case, it's going to return the index of this element, which is at stack index 2. And using stack index 2, we can access this element. So in a way, we found the element in the stack. This is how search algorithms work. This is just an instance or a criteria on which we were searching. But using search algorithms, you can have multiple different search conditions. So you can search for every element which is below a certain number, say 40 within the stack, or you can also search for elements which are at a certain index. So this is how powerful search algorithms are. Some examples of search algorithms include binary search, linear search, jump search, interpolation search, etc. Now, a vital aspect of search algorithms is pathfinding, which is used to find paths that can be taken to traverse from one point to another by finding the most optimum route. The A-star algorithm is one algorithm like this. It is a searching algorithm that is used to find the shortest path between an initial and a final point. So assume that you have a grid or a maze in this case. Your person is at the start and they have to reach the end of the maze, which is here at this point, denoted by this flag. Now using A-star algorithm, we can perform map traversal and find the shortest path which has to be taken within a map to go from the starting position to the end position. Now in this case, there are many different paths that can be taken. One option is to go along the top edges of the map. The other one is to go along the bottom edges. And the shortest path, as you can see, which takes only 4 grids, is to go directly through the center of the map, cut across its diagonal, and reach the end. Now, one major aspect of A-star algorithm is that it always takes the shorter paths first, which makes it an optimal and complete algorithm. An optimal algorithm will find the least cost outcome for a problem, while a complete algorithm finds all the possible outcomes of a problem. A-star algorithm combines all of these to find all the possible outcomes of a problem, starting with the least cost solution. Now, this is what makes A-star algorithm so handy. A-star was initially designed as a graph traversal problem to help build a robot that can find its own course, and because of this, it still remains a widely popular algorithm for graph traversal. Now, let's take a look at the basic concept behind the A-star algorithm. So we already know that A-star algorithm is an optimal and complete algorithm, but another aspect that makes it so powerful is the use of weighted graphs in its implementation. A weighted graph is nothing but a graph which uses numbers to represent the cost of taking each path or course of action. This means that the algorithms can take the path with the least cost and find the best route in terms of distance and time. In path finding algorithms, for algorithms such as A-star, you're obviously going to need a graph or a map or a path to travel, right? So for computers, we feed in something called a graph. A graph contains of two major components. First, it contains something called a node. So this is a node. And it contains something called a path. A path is nothing but a line which connects two nodes. Using this, we know the direction or the path that we have to take when we're traversing through a graph, right? So first, let's just make a very simple graph, okay? Right now we have two nodes, A and B. I'm just going to add two more, C and D. Now this connection with four nodes, A, B, C, and D, and the paths is called a graph. This whole thing is your graph. These are the graphs that these algorithms will have to travel through and find the shortest distance on. So now how do we know where we need to go in a graph? For this, we have something called a start node and an end node. So let's say our A is nothing but a start node. And our C over here, this node, is our end node, right? So now we know that we have to go from this node A all the way to this node C. In this case, it becomes very easy. I can either go from A to B to C or from A to D to C. But how do I know which path is the most optimal path or the path which has the least cost? This is made very easy by the use of weighted graphs. This is a basic graph, but in weighted graphs, all these paths between nodes have a certain weight to them or a certain number assigned to them. Like say, let's just say this is 2, the cost of this path is 3, this path has a cost of 5, and this path has a cost of 1. So now, as you can see, we assign numbers to the paths between different nodes. These numbers tell us the cost of traversing through that path. So when I take this path between A to B, I get a cost of 2 in joint only. And then I go from B to C, I have a cost of 3. Similarly, when I go from A to D, if I take this path, I have a cost of 5, and B to C will have a cost of 1. So this helps us in finding out which paths we should be taking when we're traversing from one node to the other. Now in this case, let's look at the different possible paths we can take to reach C. The first option is that we go from A to B, and this will give us a cost of 2. And then from B, we go to C, which will give us a cost of 3. Now the total cost of taking these paths can easily be obtained by finding the summation of the individual cost of these paths. So this will give us 5. All we have to do is add up the weights that each path has when we're traveling it, and we get to know what is going to be the cost of a path taken. So our path A, B to C has a cost of 5. Similarly, our path A to D and D to C has a cost of 5 plus 1 because A to D is 5 and D to C is 1, which is 6. So between 5 and 6, we know that 5 is lesser, which means that this path A to B to C is going to be a least cost path, and that is the path that we should be taking. So A-star algorithm makes use of something called weighted graphs, right? So A-star algorithm makes use of these graphs in these ways. Now let's consider that I have some other node here. Let's say that I have a node E, okay? Now B is connected to E and E is also connected to C. Let's say that the cost of taking this path B to E is 1 and E to C is 0. So now let's calculate the cost of taking the path A, B, E, and C, okay? So A to B to E to C is nothing but 2 plus 1 plus 0, which is equal to 3. When compared to A to B to C, which is nothing but 2 plus 3, which is 5, and A to D to C, which is nothing but 5 plus 1, which is 6, this path is obviously going to be the shorter path, right? But let's consider our programmer, or let's say we ourselves, don't actually want to take this path because coding for it is hard, or because it's very much isolated from the map. So we prefer to go transverse along some other nodes. And this is not a preferred node. But looking at the graph, no matter what we do, depending on how the weights are distributed, we are still going to have to go via this node. Now, to overcome this, programmers make use of something called heuristic values. What are heuristic values? So far, using a weighted graph, we've given importance to our paths. We found out which paths are easiest to take and which paths are the ones which give us a higher cost of implementation. Now, using heuristic values, we're going to do the same to our nodes. The heuristic value of a node in a graph attempts to capture the importance of that node's value within that graph. So the heuristic value is nothing but an arbitrary value which is assigned to these nodes based on the programmer's whims and needs. Just like how we have the weightage of paths, the heuristic value gives us the weight of a node and tells us how expensive it is to traverse through that node. It is represented by h of n. So now let's assign heuristic values to our graph and understand how exactly it changes how we traverse this graph, right? So let's say our initial start node A has a heuristic value of 1 and our node B has a heuristic value of say 3. Our node E, which is out of the way and which we don't really want to traverse much on, we can assign a very high heuristic value to it to ensure that it's not a path which is regularly taken. So we can assign a heuristic value of 10 to E. Let's assign other arbitrary values to the other nodes. Let's give B a heuristic value of 1 and C a heuristic value of 0. So as you can see, even though the paths over here take on a very short value, it will become a lot more expensive to traverse through E just because of its single high heuristic value as compared to the other nodes. How does having a heuristic value in a graph change how we are traversing? So after implementing the heuristic value to a graph, we now have two major values which come into play. The heuristic value, which is nothing but the value of the node, and the path weight. We can represent this as g of n, which is nothing but the weights in our weighted graph, right? So as you can see, when we're traversing from one node A to a node B, we're going to have to consider both of these values. So the cost function of a graph, or the total cost of taking a path, becomes the value of the path weight, which is given by the weighted graph, along with the heuristic value, which is assigned by the programmer or by you yourself. And this here is the basic function behind our A-star algorithm. This is the formula that A-star algorithm works on. So initially, the A-star algorithm will calculate the cost to all of its immediate neighboring nodes and choose the one which is involving the least cost. This whole process will repeat until no new nodes can be chosen and all the paths have been traversed. And then you should consider the best path among them. And how do you find the cost function? Again, we're just going to add up the heuristic value and the path value that you've taken. Now, g of n, which is the path value, is nothing but the cost of traversing from one node to another. Very obviously, this will vary from node to node. Whereas h of n, or heuristic approximation of a node's value, is not a real value, but an approximation cost that you or some other person has assigned to various nodes. Now that we know the basic concept behind the A-star algorithm, let's take a look at how exactly the A-star algorithm works with the help of a case study. So now, let's take a look at how the A-star algorithm works. To do this, we're first going to consider a weighted graph, since the A-star algorithm uses weighted graphs to make its calculation easier. So consider this to be our weighted graph. We have a node A, a node B, a node C, a node D, and a node E. Okay? Now node A is connected to node B is connected to node E is connected to node D is connected to C, and C in turn is connected to A. C is also connected to B, and A is also connected to E. So now let's assign the path values to all the different paths in our weighted graph. Let's say A to B has a path value of 1, B to E has a path value of 6, D to E has a path value of 5, C to D has a path value of 9, A to C has a path value of 10, and A to E has a path value of 2, and this has a path value of 3. Now let's assign heuristic values. Let's give A the heuristic value of 2, B the heuristic value of 5. Let's just give this a 7. Let's make this 4. And let's give C a heuristic value of 0. Okay. So now this is what a weighted graph looks like. And from basic working, you already know that the cost function of your weighted graph is nothing but the path value along with the heuristic value. So let's now say that A here is where we have to start from, and E is our target node. Okay. And this is where we are going to be starting from. Now A is a starting node, so there are 3 different paths that we can take: A to B, A to C, or A to E. So first let's consider that we take A to B. Okay. The first thing we have to consider is the heuristic value of A itself. So f of A is the first value that we're going to be considering. Right? Now f of A here is going to be the path value plus heuristic value. Now because A is the starting node and there's no other node leading up to it, it is the parent node itself. So the path value is going to be 0 because there's no path leading up to it. It's the starting node, and the starting node always has a path value of 0. Next we're going to add the heuristic value of A. In this case 2. So 0 plus 2. So f of A is 2. Right? So this is the first node that you've considered. Okay. Now after taking node A, we have 3 different options: A to C, A to E, or A to B. So the cost function of taking path A to B is going to be, so now let's find cost of taking path A to B. Right? A to B, so we have to add the graph node value plus heuristic value. The weight of taking the node A to B is nothing but 1, and the heuristic value of B is 5. So this is going to give us C. Next A to C. Sorry. Next let's get the cost of taking path A to E. Right? F of A to E. So this is going to be 2 because the cost of taking this path is 2 along with the heuristic value of E, which is 7. So this is going to be 9. And let's look at F of A to C. Now the cost of taking this is going to be 10 plus the value of C, which is 0. So this is going to be 10. Now the way how A star algorithm works is if we calculate the cost function of all the neighboring nodes and go with the node which has the least cost function. In this case, the node being B. So we're not going to take this part or this part because the cost function value is way more than the cost function value of F of A to B. So after A, we are going to be at node B. So right now, this is the direction that we've traveled in. Now when we node B to reach node E, we have 2 different options that we have to take. We can either go from B to E or we can go from B to C. Okay? The goal of A star algorithm is to always minimize the cost of the path that we're taking. So using this in mind, let's calculate F of B to C, which is going to be nothing but the cost of the path from B to C, which is 3, plus the heuristic value of C, which is 0. So this is going to be 3. Next, let's calculate the cost of B to E. Now this is going to be nothing but the path value in this case 6 plus heuristic value in this case of E, which is 7, which is nothing but 13. So again, as you can see, this is the right path to be taken. And we are not going to be taking this path because the value is really high. So the next path that we're going to be taking is this path, B to C. So now we're at node C. From node C, we can either go to A, which is not possible because we don't go back in the direction that we came from, to B, again, that's not what we're doing, or to D. So the only option that we have available is to go from C to D, right? So what we're going to do is we're going to find the cost of going from C to D. Again, this is going to be the value of the path, which is 9, plus the heuristic value of V, which is 4. The cost of traversing this path is 13, but we don't have any other path available to us because this path is already closed. You can't backtrack in A star algorithm or go back to the path that you came from. And again, we already considered A to C before, right? Like over here, we already considered A to C and we already ruled it out. So again, this is not a path that we can take. So what we're going to be doing right now is we're going to be traversing from C to D. And the cost of taking this path is 13. So now, this is the path that we're taking from C to D. Ready now. At B, again, we can go back to this path, we can go back to C. The only way we can go is E. So we're going to consider F of B to E. And this is going to be again the path that we're going to take from B to E, which is 5, plus the heuristic value of E, which is 7. This whole thing is going to be 12. Now once we're at C, our A star algorithm is going to check if this is a target node. And lo and behold, it is. So we traverse from A to E. Let's see the path we've taken. First, the starting node that we started off from was A. From there, we look at the cost of taking A to C, A to E, and A to B, and finally we decided for going from A to B. From B, again, we consider the paths B to E and B to C. We cannot consider A to B because this path is already been traveled on and it's already been considered before. Now after considering B to E and B to C, we found that B to C was the shortest path. From C, we didn't have any other option. We couldn't backtrack or go back to B, and we couldn't go to A because this path was already been considered and already considered ruled out. So the only path we could take from here was to D. And then from D, now once you arrive at node D, the only node. So now you know how the A star algorithm works. Or what is the flowchart of the A star algorithm? Now a flowchart is a picture of the separate steps of a process in a sequential order. It's basically a generic tool that can be adapted for a wide variety of purposes, and you can use it to describe various processes. In this case, this is the basic flowchart of the A star algorithm. It tells the direction of control flow within the A star program, and using this you can implement A star algorithm in any desired language of your choice. So the first step of an A star algorithm is to initialize the start node and put it in an open list. Now in this algorithm, we're going to first create 2 lists, an open list and a closed list. The open list will contain all the nodes that have been visited, but the neighbors have yet not been explored. On the other hand, the closed list contains nodes that along with the neighbors have already been visited. So the first node or a starting node is going to be put in an open list because we're exploring it. Then we're going to calculate the cost function of the starting node. From here onwards, we're going to remove this node from the open list and put it in the closed list since we've already visited it and calculated its cost function. If we're also looking at the neighbors which are surrounding this node, or if this node has many different nodes around it, then we're going to calculate the cost function for those nodes too and save the index of the node which has the smallest cost function f. Next, we're going to look at if the node we're currently on is a final node or a target node. If that's the case, we're going to terminate the algorithm and use pointers of all of our nodes to get the desired path. If that's not the case, then we're going to look at the successive nodes of n or all the nodes which come after this node which are not in the closed list. We're going to calculate the cost function of each of these neighboring nodes, remove them from the open list as they're not already in the closed list, so they're obviously not in the open list. So we're going to remove them from the open list and then we're going to put them in the closed list. And again, we're going to save the index of the neighboring node with the smallest cost function. And then this process is going to keep repeating over and over until we've reached the target node, which is where our program will get terminated. So basically what we're doing is we're going to a certain node, calculating the cost function for that node, looking at all the successive neighboring nodes of it, and going to the neighbor which has the least cost function. Now this process will again get repeated. So from this neighboring node, we're going to find all the other nodes which are connected to it, and then we are going to go to the node which has the least cost function. So using this, we're going to hop from one node to another, depending on which node has the lowest cost function. Once this is over, we're going to again take some other node and we're going to repeat this process until we found all the possible paths to a final destination node. And in this way, the A star algorithm is not only going to find the shortest path, but it's also going to find all possible paths. Now, let's see how the A star algorithm can be implemented with the help of Python. In this demo, we will use the A star algorithm to find the least cost path between various nodes in the weighted graph which is shown below. So in this graph, as you can see, we have 6 different nodes: A, B, C, D, E, and G. The weights of the paths between these nodes is denoted by these numbers in black, and the heuristic values of the nodes itself are denoted by the numbers in red. By using these values, we can find the shortest distance between any 2 nodes. Let's see how we can do this with the help of Python. So now, let's start by creating a class for the A star algorithm called the A star algo. Now in this algorithm, we're going to have to describe the open and the closed list. And to do this, we're going to be using 2 sets. So our sets are our open list and our closed list. We'll also be using 2 dictionaries, one to store distance from the starting node and another for parent nodes. And we're going to start by initializing them to 0. The open set is going to have the start node already in it. Now, we all know that the distance of the starting node from itself is 0 itself. So we're going to initialize the distance of the start node to 0. And we also know that the start node is the root node and it has no parent nodes. So the start node is its own parent node. The first step of initialization is to put the start node in the closed set to set the distance of the start node to itself as 0 and to set the start node as its own parent node. Now that we're done with the first couple of initializations, let's move on to finding all the neighboring nodes. So now we're going to have to find the neighboring nodes with the lowest value of the cost function. We also have to code for the condition of reaching the destination node. If this is not the case, we're going to have to put the current nodes in the open list, and if they're not already in it, then we're going to set the parent nodes. So that's what we're going to do. First, we're going to find the node with the lowest cost function. We're going to take the entire open set, and while the length of it is greater than 0, or basically we're not at the parent node, we're going to loop through it. We're going to go to all the neighboring nodes of the open node, and then we're going to find their cost function. Now here, this is the function that we're going to use to find the cost function. Now here, what we're going to do is we're going to calculate the heuristic value for n, and if the cost function of n is 0, or if its cost function is less than the cost function of its neighboring node, then we're going to move on to the next node, which is v. Now if n is equal to the stop node, or we've looped back and come to n itself, then we're not going to go ahead, or we're going to exit this loop, and we're going to move on to some other node. Otherwise, if the neighbor has a lower g value than the current node and is in the closed list, we're going to replace this new node as the neighbor's parent, and that's what we're doing here exactly. Now if the neighbor is not in both the lists, then we're going to add it to the open list and set its g value, and that's basically what's going on here. So let's run this for the A star algorithm. Now we're going to define a function to get the different neighbors and their distances. Next, we're going to create a function to store the heuristic values and retrieve them as and when required. Now we're going to describe a graph here. So these are all of our nodes and the nodes that they're connected to, along with the weight of their paths. So here A is connected to B and the weight of this path is 2. A is also connected to E and the weight of this path is 3. In the same way, D is connected to C and the path has a weight of 1. And GB is also connected to G and the path has a weight of 9. So here, this is what we're going to do to describe our entire weighted graph. And then we're going to find the corner A-star algorithm and give a starting node and a final node. And it very quickly finds the path between a starting node and a final node. And over here, as you can see, the best path to take would be from A to E to D and finally to G. And that brings us to the end of this video on the A-star algorithm. We hope that this video was useful to you and that you not only learned A-star algorithm in depth.
After 1 hour and a half, I'm gonna eat again, and then I'm gonna take, I think, 15 minutes to meditate. I have to be honest, I didn't pay too much attention to the videos. I'm gonna have to study more. Like I said, I don't really learn well from that structure of the videos.
With this article, you should have a solid understanding of the workings of Kruskal's algorithm, its implementation, and its various applications. Check the 20 most popular graph algorithms article next.
And now let's go to Bellman for
Introduction to Bellman-Ford's algorithm. Bellman-Ford's algorithm is a powerful tool for solving single-source shortest path problems in a graph. It is particularly useful for graphs that may contain negative edge weights. In this article, we will explore the Bellman-Ford algorithm in detail, including its time and space complexity, its applications, and its limitations. What is Bellman-Ford's algorithm? Bellman-Ford's algorithm is an algorithm for finding the shortest path between a given source vertex and all other vertices in a weighted graph. It is a dynamic programming algorithm that uses a relaxation process to gradually improve the estimates of the shortest path from the source vertex to each other vertex in the graph. The algorithm starts by initializing the distance from the source vertex to itself as 0, and the distance to all other vertices as infinity. It then repeatedly relaxes each edge in the graph, updating the distance estimates as necessary. The algorithm stops when it has completed V1 iterations, where V is the number of vertices in the graph. Time and space complexity. The time complexity of Bellman-Ford's algorithm is O, V, where V is the number of vertices in the graph and E is the number of edges.
let me verify that.
The time complexity of Bellman-Ford's algorithm is O, V.
Let me see if I... Yeah, so it is correct. According to this thing. OV. I don't pay too much attention to the exact time complexity of algorithms because I think it's sufficient to have an intuitive understanding based on the way that they work of the time space that it takes. But I think I'm going to improve with this with time as well, especially on the space, I think, because I'm not very good at understanding the space that the algorithm takes. But time, I think, is easier to think about it. Yeah, I think I'm gonna trust that it is correct.
Of Bellman-Ford's algorithm is O, V.
Oh, I forgot to... Oh no, I checked this out, but then I left the tab open to search for more stuff.
Applications of Bellman-Ford's algorithm. Bellman-Ford's algorithm has a wide range of applications, including limitations of Bellman-Ford's algorithm. While Bellman-Ford's algorithm is a powerful tool for solving shortest path problems, it does have some limitations. These include Python implementation, def Bellman-Ford, graph,
Yeah, this one I already looked into it. I watched the videos as well. So I think there is a high chance that this is correct.
Conclusion. Overall, Bellman-Ford's algorithm is a powerful tool for solving single-source shortest path problems in a graph. It is particularly useful for graphs that may contain negative edge weights and can be used for a wide range of applications. However, it does have some limitations and may not be the best choice for certain types of graphs or applications.
The next one. I think it's breadth. Yeah, breadth first search. I think this one and the next, which is depth first search, is easy, I think, to understand.
However, it does have some limitations and may not be. Breadth First Search, a comprehensive guide. Breadth First Search, BFS, is a widely used algorithm in computer science, specifically in the field of graph theory and network analysis. It is a method of traversing a graph or a tree data structure in which the nodes are visited in a breadth-wise manner, rather than depth-wise. In this article, we will provide a comprehensive guide on the Breadth First Search algorithm, including its use cases, implementation, and variations. What is Breadth First Search? BFS is a graph traversal algorithm that visits all the nodes of a graph in breadth-wise order. It starts at the root node and explores all the neighboring nodes at the present depth before moving on to the nodes at the next depth level. The algorithm uses a queue data structure to keep track of the nodes to be visited. The nodes are dequeued from the front of the queue and inqueued at the back of the queue. Use cases of Breadth First Search. BFS has several use cases in computer science, some of which include shortest paths. BFS can be used to find the shortest path between two nodes in a graph. The algorithm guarantees that the first time a destination node is visited, the path to it is the shortest possible. Connectivity. BFS can be used to check whether a given graph is connected or not, implementing Breadth First Search. BFS can be implemented using a queue data structure. The algorithm starts at the root node and visits all the neighboring nodes at the present depth before moving on to the nodes at the next depth level. The basic steps for implementing BFS are: create a queue and inqueue the root node. Dequeue a node from the front of the queue and visit it. Inqueue all the unvisited neighbors of the dequeued node.
Yeah, I think this is really easy to understand, and it is correct here. I'm gonna go fast through
Variations of
this one.
Breadth First Search. There are several variations of the BFS algorithm, some of which include bidirectional search. This variation of BFS is used to find the shortest path between two nodes in a graph more efficiently. Instead of starting at one node and traversing the entire graph, bidirectional search starts at both the source and destination nodes and moves towards the middle of the graph. This reduces the amount of nodes that need to be traversed and can greatly decrease the time it takes to find the shortest path. Uninformed search. This variation of BFS is used when the goal node is not known. The algorithm explores the entire graph without any prior knowledge of the goal node. This can be useful in certain applications such as searching for a specific item in a large dataset. Cost-limited search. This variation of BFS is used when the cost of traversing certain nodes is known. The algorithm explores the graph while keeping track of the total cost of traversing each node. This can be useful in certain applications such as finding the shortest path in a graph with weighted edges. Iterative deepening search. This variation of BFS is used when the depth of the goal node is not known. The algorithm starts at the root node and explores to a certain depth, before moving on to the next depth level. This can be useful in certain applications such as searching for a specific node in a deep tree structure. Conclusion. Breadth First Search is a powerful algorithm that can be used in a variety of applications in computer science. Its ability to find the shortest path, check for connectivity, detect cycles, and more make it a valuable tool for solving problems in the field of graph theory and network analysis. We hope this guide has provided a comprehensive
Yeah, obviously, I'm not going to be able to implement all of these algorithms at the top of my head, because it's different understanding how it works and looking at things this way. It's a lot easier than to come up with the algorithm yourself, but it is sufficient for me to know how it works and to verify. So I think it doesn't matter, I think. So yeah, doing things like this allows me to go faster. But obviously, I'm not gonna be able to implement all of them at the top of my head, off the top of my head. If I encounter a problem, in order to do that, I think I would have to train to do LeetCode or some exercises to ingrain. But I do feel like my understanding of how the algorithms work is increasing a lot by doing this. It's a lot more clear in my mind now how these algorithms work than it was before. But I can still tell that it would be difficult for me to come up with the solution myself if I had to. And that's the issue that I have with the videos as well that talk about this, because they talk more about the concept and not how do you approach the problem when you are coding yourself. Like how do you think about which kinds of things to use? In breadth first search I think is easy, but for the other ones, like for example the disjoint set, of how do you think about the functions and how to structure things. But I think it is a lot more clear in my mind now. And the only thing here is that this get neighbors function doesn't exist here, but I thought it's not necessary to put the function because it's kind of intuitive, I think, but maybe I'm wrong about that, because it pretty much means that it's like kind of pseudocode. You would have a function outside of this that gets the node from the current node, but this is just for illustration purposes. That you visit, for the node you're visiting, you get all the neighbors and then you append on the queue, so later on you can pop them and go traverse the graph that way. So I think it's kind of intuitive there. That's why I didn't put any explanation there. But maybe I should, maybe I'll change in the future. But for now, I think I'll leave it like that.
Depth first search, an in-depth look at a classic algorithm. Depth first search, DFS, is a popular algorithm for traversing and searching through graphs and trees. It is a simple and straightforward algorithm that can be used to solve a wide range of problems, from finding the shortest path in a maze to checking for the existence of a cycle in a graph. In this article, we will take an in-depth look at the DFS algorithm, its time and space complexity, and its various applications. How the DFS algorithm works. The DFS algorithm starts at a given vertex, or node, in a graph and explores as far as possible along each branch before backtracking. The algorithm uses a stack to keep track of the vertices to be visited. Initially, the starting vertex is pushed onto the stack, and the algorithm then repeatedly pops a vertex from the stack and visits it. If the popped vertex has any unvisited adjacent vertices, they are also pushed onto the stack. The algorithm continues in this way until the stack is empty, at which point all vertices in the graph have been visited. It is important to note that the DFS algorithm can be implemented using both recursion and iteration. In the recursive implementation, the algorithm visits a vertex and then recursively calls itself on each unvisited adjacent vertex. In the iterative implementation, the algorithm uses a stack to keep track of the vertices to be visited, as described above. Time and space complexity. The time complexity of the DFS algorithm is O, V plus E, where V is the...
Yeah, and I remember on this one that I was confused about the difference between using the stack and the queue, because the example it shows, it pretty much just changes the code to use pop for the last, or yeah, the last item in one of them, but use pop to get the first item in another one, but it's using a list on both of them. And the difference is in the way that you put and remove items. If the first item you put is the last one that you take out, then it's considered to be a stack. And if the first item you put is the one that you take out, it's considered to be a queue. And that this ordering of the ones that you put and remove from the list is what makes the difference in the algorithm. So I think depth first search uses the stack principle, which is to put the first item that it puts is the last one that it removes, and that's why usually you see implemented with recursion. But for breadth first search, you use the queue, which means that the first item you put is the one that you remove.
The time complexity of the DFS algorithm is O, V plus E, where V is the number of vertices and E is the number of edges in the graph. This is because the algorithm visits each vertex and each edge exactly once.
But if you're just looking at the code and you don't understand really well, then it's confusing because you can use just a simple list, and the only difference you're gonna have is the way that you are popping or pushing items into the list. So it can be confusing because depending on which method you use, it changes the algorithm. Because you have to imagine that the way that you are inspecting the nodes depends on the flow of information from the list. So the items you remove and put in the list, because that maps to the way that the algorithm is going through the nodes of the graph. So there's this correlation between, like, the data structure is the flow of information inside of the graph network.
This is because the algorithm visits each vertex and each edge exactly once. The space
And I think that's why A star is kind of difficult to understand, because it's a combination of both breadth first search and depth first search, in the sense that you use a heuristic function to determine the flow of information inside of the graph. So it gets more complex because you have to understand how the heuristic function works and how do you keep track of the nodes visited in order to maintain the integrity of the function, let's say, that determines the flow of information. And I think that's going to be the same with all algorithms. I think that's one of the fundamental principles of these graph algorithms. At one end of the spectrum, you have breadth first search, and the other you have depth first search, and that creates a pyramid. And the flow of information depends on the circumstance. So the level of difficulty of the algorithm increases with the nuance of complexity of the flow of information inside of the graph structure. And that's going to depend on the data structures you're using to map out the search.
The space complexity of the DFS algorithm is O, V, as the algorithm uses a stack to keep track of the vertices to be visited, and the maximum size of the stack is
Yes, so I think one fundamental principle would be the dimensions of the graph are equivalent to the amount of iterations you do, because the more dimensions, the more iterations, because you have to go over all of the nodes in all of the dimensions. And the other principle would be this gradient of the flow of information, where you can have horizontal or vertical, or any, depending on how many dimensions you have, is going to increase the paths you have as well. And that's going to determine the shape of the data structure that is going to dictate the flow of information, which for the optimal and most efficient search, in most cases, is going to be a combination of both situations, which makes it more difficult to understand because it's the paradoxical point that encapsulates both sides of the polarity.
The space complexity of the DFS algorithm is O, V, as the algorithm uses a stack to keep track of the vertices to be visited, and the maximum size of the stack is V. Applications of DFS. Path finding. One of the most common uses of DFS is to find a path between two vertices in a graph. The algorithm can be modified slightly to keep track of the path taken from the starting vertex to the current vertex, and the path can be returned once the target vertex is reached. Topological sorting. DFS can be used to perform a topological sort on a directed acyclic graph, DAG.
Yes, so the only thing that would be left for me to write the archetype of the graphs would be to understand how the nuance of the problem dictates the shape of the data structure that is used to dictate the flow of information for the graph, and to derive the physical principles that make that connection, I think. Because the data structures are mapping the physical principles, so the nature of the problem is going to be correlated to the data structure, which is going to allow me to abstract or extract the fundamental principles that make up the search most of the time, and what changes between them in the data structure, which I guess is going to be the distribution of queue and stack, and then a combination of both of them through some heuristics functions, depending on the problem, I think.
Topological sorting. DFS can be used to perform a topological...
And the number of the dimensions of the graph.
Topological sorting. DFS can be used to perform a topological sort on a directed acyclic graph, DAG. A topological sort is a linear ordering of the vertices in a graph such that for every directed edge, U, V, vertex U comes before vertex V in the ordering. Cycle detection. DFS can be used to check whether a given graph contains a cycle or not. The algorithm can be modified to keep track of the visited vertices, and if an already visited vertex is encountered again, a cycle is detected. Connected components. DFS can be used to find the connected components of an indirect graph. An indirect graph is said to be connected if there exists a path between any two vertices in the graph. By running DFS from each unvisited vertex, all the connected components of the graph can be found. Solving mazes. DFS can also be used to solve mazes. The algorithm can be modified to prioritize moving in one direction until a dead end is reached, at which point the algorithm backtracks and tries a different direction. Python implementation. Def DFS, graph, V, visited V equals true print, V, end equals, for neighbor in graph V, if not visited neighbor, DFS, graph, neighbor. Visited, hashtag driver code, hashtag create a sample graph represented in an adjacency list graph equals 0.
Yeah, this implementation is pretty easy to understand.
In this example, the DFS function takes in 3 parameters, the adjacency list representation of the graph, the starting vertex, V, and a list to keep track of which vertices have been visited. The function sets the current vertex as visited, prints it, and then recursively calls itself for each unvisited neighbor of the current vertex. Conclusion. In conclusion, the depth...
Now let's go to the next one. Yeah, this is the difficult one.
The A** algorithm, a comprehensive guide. The A** algorithm is a powerful tool for solving problems in computer science, particularly in the field of artificial intelligence and pathfinding. It is widely used in a variety of applications, including video games, robotics, and self-driving cars. The A** algorithm works by combining the strengths of 2 other popular algorithms, Dijkstra's algorithm and the best first search algorithm. Dijkstra's algorithm is a popular algorithm for finding the shortest path between 2 points in a graph, while the best first search algorithm prioritizes searching the most promising nodes first. The A** algorithm combines these two approaches by using a heuristic function to estimate the distance between the current node and the goal node. This heuristic function, also known as the cost function, takes into account both the actual distance traveled and an estimate of the distance still remaining to the goal. Advantages of the A** algorithm. One of the major advantages of the A** algorithm is its efficiency. Because it prioritizes the most promising nodes, it is able to find the shortest path much more quickly than other algorithms like Dijkstra's. Additionally, the A** algorithm is highly versatile and can be used in a wide variety of applications. It is particularly useful for path finding in video games, as it allows for smooth and realistic movement of characters and objects. The A** algorithm is also useful in robotics and self-driving cars, as it allows for navigation through unknown and dynamic environments. Implementing the A** algorithm. Implementing the A** algorithm can be a bit tricky, as it requires a good understanding of data structures and algorithms. However, with a bit of practice and study, it is definitely possible to master. Here are a few basic steps to implementing the A** algorithm. Create the open and closed lists. Initialize the starting node and add it to the open list. Select the node with the lowest cost from the open list and move it to the closed list. Evaluate all of the neighboring nodes and update their costs accordingly. Repeat steps 3 and 4 until the goal node is reached or the open list is empty. It is important to note that the heuristic function is a crucial component of the A** algorithm and can greatly affect the performance of the algorithm. It is important to choose a heuristic function that accurately estimates the distance to the goal while also being computationally efficient. Python
So this gets the current node and then loops through the neighbors. Well, so far currents. And this is the part that I didn't understand because in the first iteration it's not gonna have the node in the cost so far dictionary. Graph, not cost.
In this example, the ASTA function takes in 3 parameters, the grid represented as a graph, the starting point, start, and the goal point, goal. The algorithm uses a priority queue, implemented as a heap, to store the nodes to be explored, where the priority of each node is the estimated total cost to reach the goal, the sum of the cost so far and the heuristic cost to the goal. In each iteration, the node with the lowest estimated cost is popped from the priority queue and its neighbors are explored. If a neighbor has not been visited before or if a shorter path to it is found, its cost is updated and it is added to the priority queue. Conclusion. The A** algorithm is a powerful and versatile tool for solving problems in computer science. Its efficiency and ability to find the shortest path make it a popular choice in a wide variety of applications, including video games, robotics, and self-driving cars. While implementing the A** algorithm can be challenging, with a good understanding of data structures and algorithms, it is definitely possible to master. One important aspect to keep in mind when implementing the A** algorithm is the choice of heuristic function. A well-designed heuristic function can greatly improve the performance of the algorithm and help it find the shortest path more efficiently. Another important consideration when using the A** algorithm is the type of graph being used. The algorithm is well suited for graphs with a small number of nodes and edges, but can become less efficient as the number of nodes and edges increases. It's also worth noting that the A** algorithm can be modified to accommodate different types of search problems. For example, it can be modified to handle multiple goals or handle different types of terrain. Overall, the A** algorithm is a valuable tool for solving problems in computer science, and its versatility and efficiency make it a popular.
I think I understand the concept, but I don't understand the nuance here. Like the new cost here is the thing that is puzzling me. And also this thing here. It looks like ChatGPT is off. So I think they're gonna start charging now. Other thing I have to think about is if it is worth to get ChatGPT because there are other models out there as well. They might be better. And I also heard that, or saw that Google is gonna come up with their own thing as well. Just trying one more time to see if it works. Because I had this before and then I tried again and then it worked. It looks like it did work. Let's see if it works. Oh no. I think it's gonna give me the same implementation probably. I'm just gonna ask what does the line mean? So it pushes the priority to the queue, which is the cost based on the heuristic function. I think I understand everything, just this line here that I'm confused about. Oh, I didn't see this thing here. That's why. Oh, now it makes sense. So it initializes the previous to none, kind of in the same way that the linked list, the last element in the linked list is gonna be none, but the other way around. Because you're traveling in reverse, let's say. So the came from is none in the first, the cost is 0 for the first, and then it uses that to get the cost. And I think this, I'm also gonna ask to explain what this is here, but it's probably a function to, but I'm gonna put the explanation of this function here. I'm gonna ask and then put the explanation. So if the previous cost is lower than the current cost of the node, it goes through this. Bigger than, yeah, to increase the cost, I think. Because otherwise it doesn't want the path should be on the priority, I think. Or maybe not understanding really well. Yeah, not, so this stops from going to the same node, and then this I don't understand really well. I think so. The current node is the next, and the new cost is the one that's the weight for the previous, the cost for the previous node, based on this thing here, cost so far plus current cost. So if this is smaller than the cost so far next, which is the cost of the current node, yeah, but how it would be smaller if it's always increasing? Cost so far from the start node 0. Then graph cost, which would be the weight of the edge for, yeah, this is the weight of the edge for from the current one to the next. That's the new cost. Volume cost so far next, which is the cost of the path to that point. I think I understand, just trying to make sure that makes sense on my mind. I'm pretty sure that the code is correct. I'm just trying to make sure that I understand. So it turns the next one into the cost of the previous one to update the thing. Makes sense. Then it posts on their priority the new cost plus the heuristic, which is the function that optimizes the path. And I guess it passes the edges here. Like, how does this work? Because if B is a node, then this doesn't make sense. So maybe I'll ask this question. Yeah, but it's A is the goal here. So if yeah, and next is the next one. So if next is a coordinate, it means that it can't be a node or a single value in the other ones. That's what it doesn't make sense to me, unless it's the edge between the nodes and the value is the weight. Then I guess that would make sense, but I'm gonna put some music because it's probably gonna take some time. Obviously, I want to make sure that I understand this. Oh, fuck. I think these two parts here I understand, and these ones are a little bit difficult to understand, but I think I understand as well. So the new cost is the cost to go to the next one. It's the current cost plus the cost to go to the next one. And then it updates the dictionary with the value of the node and makes it equal to the new cost. Then the priority is gonna be the new cost plus the whatever the heuristic is, and then you push to the heap the priority with the value of the next node, so that you keep traversing. And then you update the came from with the current one, which is the node that was behind, let's say, the previous node. So I think this part makes sense to me. The one that I don't know 100% is this one, and also how is it possible that it accepts the node in the heuristic function, but then it unpacks into coordinates here? Because the node is supposed to be a single value, so that doesn't make sense to me. Like, if it was only the goal, then it could make sense because it doesn't say anything about what the goal is. So the goal could be a tuple of coordinates, x and y. But then because there's this next here, next is supposed to be the current node, which is supposed to be a value in my mind. Because the way that it is being used here to update the dictionary, but it might be the case that it is a tuple and then the key is the tuple of the dictionary. I know that, I think that tuples are immutable in Python, so that's why it might be possible for you to use them as keys. But I know that you can't use the lists as keys because you can't use immutable values as keys in Python. So I think it would make everything makes sense if the next is a tuple with the coordinates that represents the edge, let's say. I'm going to make a simple script here to see if it works. To put a tuple just to make sure, but I think it is possible. Yes. Yeah, it is possible to have a tuple as a key. Created a simple script and just to verify. So it might be the case that this is a tuple. I think it does make sense because you're looping through the neighbors. Yeah, but current is supposed to be a value. Neighbors current, because current is a star. Oh, but it might be this thing here. Yeah, I think that's, yeah, because you're popping from the queue and you're getting the tuple. Now it makes sense. So current is 0 and start, and because this is the key on the graph, it gets the neighbors. I think it makes sense now. And then the heuristic calculates the one coordinate minus the other and takes the absolute value and then sums them. And then increases that to the new cost. I think I understand now how it works. But I think I'm gonna put that in the description of the code to explain. Like the stuff that I just talked about. Because other people are gonna struggle to understand that as well. I'm gonna put in this example. The first current node value in the line is I'm pretty confident that this is what's happening, so maybe I'm wrong, and hopefully someone corrects me in the future. But I think that's accurate. So the first current node in the line And next, you'll also be a tuple containing the coordinates or the value of the neighbor of the first nodes. These tuples are used as keys in the dictionaries. Keep track of nodes visited and also to calculate the cost of going to them in the heuristic function. This is still a little bit confusing to me. So cost so far is it takes from the current one, which is the current node being visited, or the current nodes, the node that was visited before. So it gets the cost to the node that was visited before using the dictionary here. Plus, then calculates the cost for the next node. So gets the current cost. So it first checks to see if the next is already on cost so far. Or if new cost. And this is the part that is confusing. Oh, cost so far. The next is the next node. It's confusing me because it starts with the zero here with the start node. That's why I'm confused. Because in the beginning they are both the start because they, even though they are different. Because one of them is coming from here, the other one is here. It's on the dictionary. And so the value of the tuple in the dictionary is going to be 0. But then the current in the first iteration is also this one, because it's the same node. Next not in cost so far. Yeah, but then what is cost so far next? In the first iteration. Because the node doesn't exist. What's so far next? Like the value doesn't exist on the dictionary. So maybe it is wrong. Yeah, because how you would test? Because if it's not on the cost so far, how do you get the value? Doesn't make sense. Oh, because it is not. It does make sense. So it's gonna pass this condition, and then it's not gonna evaluate this one in the first iteration. So it doesn't make sense. And then here is gonna add the next node to the thing. And then if it is, it's gonna check if the cost of it is greater than the new cost. Because if it is, then it has to update the cost. Oh, I think I get it now. Okay, so it does make sense. First quarter, will also be a tuple containing the coordinates for the value of the neighbor of the first node. Use the keys in the dictionary to keep track of nodes visited and also to calculate the cost of going to them with the heuristic function. The first iteration, the next, all of this nodes. The costs, so yeah, it's updated. If condition. First current node value in the line for next blah blah will be zero start, and next will also be a tuple containing the coordinates for the value of the neighbor of first node. These tuples are used as keys in the dictionaries to keep track of nodes visited and also to calculate the cost of going to them with the heuristic function. The first iteration, the cost of far doesn't contain the node in the dictionary, so it doesn't contain the next node in the dictionary, so it gets updated after the if condition should be the value of the new cost. After that, a heuristic function is used to determine that what will be the priority of visiting the next node based on the delta of distances of coordinates from the two nodes, which are both tuples containing the coordinates for the node. This part's a little bit confusing. I want to say that the node is a coordinate, a tuple with the coordinates. What I'm calling a node is a tuple. Condition should be the value of the new cost. After that, a heuristic function is used to determine what will be the priority of visiting the next node based on the delta of distances of coordinates from the two nodes. In this case, both next and tuples that contain the coordinates for the specific node. After the heuristic function is used to determine what will be the priority of visiting the next node based on the delta of distances of coordinates from the two nodes. In this case, both go and next are tuples that contain the coordinates for the specific node. And then they are pushed into the queue to determine which one is going to be visited next. As if they already exist on the cost so far is only going to go if the new cost is lower than the current one. They are done. Appended to the heap or the next iteration. New costs. Condition. Make sure that priorities the heap are only updated if the cost of the next node is bigger than the cost. Next not in cost so far. Actually, this is still confusing to me. I'm gonna spend more time trying to clarify. Checks whether the next node is not in the cost of far dictionary. The new cost of getting that to that node is lower than the current cost of getting to that node. Oh, I get it. So the new cost is the current cost is the one that it was cached before. If the algorithm already passed through the node. if the existing cost. Right, sure. I think I understand now. So it's pretty much what I wrote there. Makes a lot of sense. It's very hard to understand in the beginning, but after it clicks, it makes sense. It's difficult because the R statement is confusing a little bit. In this example, the A star function takes in 3 parameters: the grid represented as a graph, the starting point start, and the goal point. The algorithm uses a priority queue implemented as a heap to store the node to be explored, where the priority of each node is the estimated total cost to reach the goal, the sum of the cost so far, and the heuristic cost to the goal. In each iteration, the node with the lowest estimated cost is popped from the priority queue and its neighbors are explored. If a neighbor has not been visited before, or if a shorter path to it is found, its cost is updated and is added to the priority queue. Also, I don't think I need to explain, because I think these comments here are enough to explain this thing here. The first current node value in the line for next will be 0 start, and next will also be a tuple containing the coordinates for the value of the neighbor of the first node. These tuples are used as keys in the dictionaries to keep track of nodes visited and also to calculate the cost of going to them with the heuristic function. The first iteration, the cost so far, doesn't contain the next node in the dictionary, so it gets updated after the if condition to be the value of the new cost. After that, a heuristic function is used to determine what will be the priority of visiting the next node based on the delta of distances of coordinates from the 2 nodes. In this case, both go and next are tuples that contain the coordinates for the specific node. I think that's good enough, probably. In this case, both. They are then appended to the heap for the next iteration. The new cost greater than cost so far next condition makes sure that the priority and heap are only updated if the existing cost of going to the next node is bigger than the new cost. The reason why is because if the code reaches that point, it means that the path to the next node already existed, because the condition next node in cost so far was evaluated to false. Which means that it is in cost so far, which means that the node was already visited at some point. So if the new cost is lower, it updates the priority and values, otherwise it skips that path. I think that's good enough. And I finally understand how this works. This is what I mean with the videos, and the reason why they are not really good for my style of thinking, I think. Because I already understand the concept really easily, with the whole idea of the algorithm, but to understand these nuances here, that it gets kind of confusing because you don't know at first, like which thing is which. I guess it's hard to, because you don't have the values here, so it's hard to visualize what each thing is gonna be. And then you're gonna be careful to not make the wrong assumption over what's next and what's the goal. So I guess that's why it becomes hard to understand, I think. Yeah, but now I think it makes sense. Yeah, I'm gonna do this.
The first current node value in the line. In this example, the ASTA function takes in 3 parameters, the grid represented as a graph, the starting point, start, and the goal point, goal. The algorithm uses a priority queue, implemented as a heap, to store the nodes to be explored, where the priority of each node is the estimated total cost to reach the goal, the sum of the cost so far and the heuristic cost to the goal. In each iteration, the node with the lowest estimated cost is popped from the priority queue and its neighbors are explored. If a neighbor has not been visited before or if a shorter path to it is found, its cost is updated and it is added to the priority queue. The first current node value in the line, for next in graph.neighbors, current, will be 0, start, and next will also be a tuple containing the coordinates for the value of the neighbor of the first node. These tuples are used as keys in the dictionaries to keep track of nodes visited and also to calculate the cost of going to them with the heuristic function. In the first iteration, the cost so far doesn't contain the next node in the dissidonary, so it gets updated after the if condition to be the value of the new cost. After that, a heuristic function is used to determine what will be the priority of visiting the next node based on the delta of distances of coordinates from the 2 nodes. In this case, both goal and next are tuples that contain the coordinates for the specific node. They are then appended to the heap for the next iteration. The new cost. The reason why is because if the code reaches that point, it means that a path to the next node already. The new cost. The reason why is because if the code reaches that. The reason why is because if the code reaches that point, it means that a path to the next node already existed because the condition, next not in cost so far, was evaluated to false. So if the new cost is lower, it updates the priority and values, otherwise it skips that path. Conclusion. The A** algorithm is a powerful and versatile tool for solving problems in computer science. Its efficiency and ability to find the shortest path make it a popular choice in a wide variety of applications, including video games, robotics, and self-driving cars. While implementing the A** algorithm can be challenging, with a good understanding of data structures and algorithms, it is definitely possible to master. One important aspect to keep in mind when implementing the A** algorithm is the choice of heuristic function. A well-designed heuristic function can greatly improve the performance of the algorithm and help it find the shortest path more efficiently. Another important consideration when using the A** algorithm is the type of graph being used. The algorithm is well suited for graphs with a small number of nodes and edges, but can become less efficient as the number of nodes and edges increases. It's also worth noting that the A** algorithm can be modified to accommodate different types of search problems. For example, it can be modified to handle multiple goals or handle different types of terrain. Overall, the A** algorithm is a valuable tool for solving problems in computer science, and its versatility and efficiency make it a popular choice in a wide range of applications. With a good understanding of data.
Yeah, let's go to the next one. I think at this pace I'm probably not going to be able to finish them today, but I think it's fine. I want to be careful to be balanced and not go too fast or too slow on any of them. But I don't want to be careful to not force myself to go too fast, because then I might not, I don't know what the right expression is, but to leave articles that may contain wrong information. I don't want to do that, obviously.
Floyd-Warshall algorithm, a comprehensive guide. Introduction. The Floyd-Warshall algorithm is a well-known algorithm for solving the all-pairs shortest path problem in a graph. It is a dynamic programming algorithm that can be used to find the shortest path between any 2 vertices in a graph, even if the graph contains negative edge weights. In this article, we will discuss the Floyd-Warshall algorithm in detail, including its time complexity, space complexity, and various applications. The all-pairs shortest path problem. The all-pairs shortest path problem is the problem of finding the shortest path between all pairs of vertices in a given graph. This problem is important in many real-world applications such as transportation systems, social networks, and communication networks. There are several algorithms that can be used to solve this problem, including the Bellman-Ford algorithm, the Dijkstra algorithm, and the Floyd-Warshall algorithm. The Floyd-Warshall algorithm. The Floyd-Warshall algorithm is a dynamic programming algorithm that can be used to find the shortest path between all pairs of vertices in a graph. The basic idea behind the algorithm is to iteratively relax the edges in the graph, starting with the shortest paths between the vertices that are directly connected and gradually increasing the number of intermediate vertices in the path. The algorithm starts with a matrix of distances, where the distance between two vertices is initialized to the weight of the edge between them if there is an edge, and infinity otherwise. The algorithm then iteratively updates the matrix by relaxing the edges, using the following formula. distij equals min, distij distik plus distkj, where distij is the shortest path between vertices I and j, and k is an intermediate vertex. The algorithm terminates when there are no more updates to the matrix, at which point the matrix contains the shortest path between all pairs of vertices in the graph. Time complexity and space complexity. The time complexity of the Floyd-Warshall algorithm is n-3, where $n$ is the number of vertices in the graph. This is because the algorithm performs n-3 iterations, and each iteration takes
Now let me
time.
remove the n there. So it's pretty similar to the previous ones, but the difference is it uses a matrix representation, and then instead of starting with all of them to infinity, it only starts the ones that don't have edges to infinity.
This is because the algorithm performs n-3 iterations, and each iteration takes n time. The space complexity of the Floyd-Warshall algorithm is n-2, where n is the number of vertices in the graph. This is because the algorithm uses a matrix of size n-2 to store the distances between the vertices. Applications. The Floyd-Warshall algorithm has many important applications in various fields, including network design. The Floyd-Warshall algorithm can be used to find the shortest path between all pairs of vertices in a communication network. This can be used to optimize the design of the network, in order to minimize the total length of the cables or the number of repeaters needed. Transportation systems. The Floyd-Warshall algorithm can be used to find the shortest path between all pairs of cities in a transportation system. This can be used to optimize the routes of the vehicles, in order to minimize the total distance traveled. Social networks. The Floyd-Warshall algorithm can be used to find the shortest path between all pairs of people in a social network. This can be used to optimize the spread of information or influence in the network. Image processing. The Floyd-Warshall algorithm can be used in image processing to find the shortest path between pixels in an image. This can be used to create a path that connects 2 points in an image, such as for image segmentation or object recognition. Computer networks. The Floyd-Warshall algorithm can be used to find the shortest path between all pairs of nodes in a computer network. This can be used for routing, in order to minimize the delay or cost of transmitting data through the network. Bioinformatics. The Floyd-Warshall algorithm can be used to find the shortest path between all pairs of amino acids in a protein structure. This can be used to analyze the stability or flexibility of a protein structure. Python implementation. Def Floyd-Warshall.
And so I guess the way that you create the matrix is you just get all of the nodes by the nodes, and that's what adjacency matrix is. So you have all the nodes as rows and all the nodes as columns, and then when there isn't an edge, the weight's going to be infinity, and if there is an edge, then the weight is the edge, and then you just do this. But I'm not really sure if this is a brute force solution or if it is the optimal solution. It seems like it is the brute force solution because it's using this 3 nested loops, and there might be a better way. So I think I'm gonna use ChatGPT again to see if there is a better approach. But I think that this one is really easy to understand how it works.
Conclusion. The Floyd-Warshall algorithm is a well-known and widely used algorithm for solving the all pairs shortest path problem in a graph.
Probably
has
go
a time complexity
faster to this one. Yeah, so it's the same thing. So I'm gonna look here. Yeah, so yeah, this one's pretty easy. I'm gonna go to the next one. It looks like this is probably the best. I'm gonna look in Geeks for Geeks as well. It's slightly different, but different, but pretty much the same thing. So let's go to the next one. Johnson's. Let's see how. I think after the next break, I'm gonna stay for another 1 hour and a half, and then I'm gonna stop because I'm already getting tired. It's like my headphones are really annoying to use after some time. So, yeah. It's not. I'm not actually tired. I think I can keep going, but the headphones are annoying me. So I'm probably gonna stop after the next break. I take either 1 hour or 1 hour and a half, and then I stop.
Johnson's algorithm demystified, a beginner's guide to graph theory. Introduction to Johnson's algorithm. Johnson's algorithm is a widely used
And
method.
I think after I stop streaming, I'm probably gonna do some of them off stream as well, because I wanna try to finish this as fast as possible. Let me see how much I have left. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, 12. Okay. So I think if I can get down to 8 today, or maybe 7 or around that, then tomorrow I'll definitely finish this. Obviously, it's gonna depend on how hard each one of them are.
Johnson's algorithm is a widely used method for finding the shortest paths between all pairs of vertices in a weighted, directed graph. This algorithm is an improvement over the Floyd-Warshall algorithm, which has a time.
And after I finish with these graph algorithms, the next one that I'm gonna do is gonna be trees, and I already separated here in this list. I'm gonna do the same way that I did this one. This one I committed at first because I'm participating in a meeting once a week where the guy helps me. It helps a bunch of people actually. It's a Zoom meeting with the marketing and SEO and those kinds of things. So I wanted to wait. I wanted to commit because of that, because of the meeting, to see what he thinks of the blog. So, and I made some changes, and then I didn't want to think about how I was gonna put in a different branch the thing. So these are already on the official, but on the next ones I'm gonna put the articles on a different branch, and I'm only gonna commit them after reviewing them. But I'm gonna do them in the same way that I did here, I think. So use ChatGPT, then produce a bunch of them, and then review them one by one, and then update them, merge the. So maybe I'll do in different batches, actually, now that I think about it, because it's probably better to update as fast as possible. Or I'll do the other way that I was talking about, where I'm gonna put on the other folder. I think that's better, probably. I'll put it on this folder. Yeah, so what I'm gonna do is generate all of the articles. I'm gonna do 20. I think I'm gonna do 20 for each data structure here, each one of these, if it is possible. I'm not really sure if all of them have 20 different algorithms. But then after I do that, then I'm gonna put them on a file here. I'm gonna create all the articles only with ChatGPT, and then on stream I'm gonna review the articles from ChatGPT and correct the information that is not wrong, and also occasionally add one thing or two that I think it might be helpful if I think that the article is not good enough. And after I reach, I think I wanna, because I don't wanna have only articles in one category. So, and this is just programming. So after I have several different articles on all the main categories, then I'll think about the creating other articles that are synthesis of the ones that I already have, or creating more original things. I think that's a good mix between doing stuff with ChatGPT and stuff on my own.
This algorithm is an improvement over the Floyd-Warshall algorithm, which has a time complexity of O, n-3, while Johnson's algorithm has a time complexity of O, n-2 long. This makes it a more efficient solution for large graphs. How does Johnson's algorithm work? The algorithm starts by adding a new source vertex to the graph, connecting it to every other vertex with a weight of 0. This step is known as reweighting the graph. Next, the algorithm uses Dijkstra's algorithm to find the shortest paths from the new source vertex to every other vertex in the graph. The weights of the edges in the original graph are then adjusted by subtracting the shortest path weight from the new source vertex to the vertex at the other end of the edge. This step is known as dereweighting the graph. The final step of the algorithm is to use the Bellman-Ford algorithm or the Dijkstra's algorithm to find the shortest paths between all pairs of vertices in the dereweighted graph. These shortest path lengths can then be used to find the shortest paths in the original graph by adding the shortest path weight from the new source vertex to the vertex at the other end of the edge. Implementation of Johnson's algorithm. The implementation of Johnson's algorithm is relatively straightforward. The first step is to initialize the new source vertex and connect it to every other vertex with a weight of 0. Next, Dijkstra's algorithm is used to find the shortest paths from the new source vertex to every other vertex in the graph. Once the shortest paths have been found, the weights of the edges in the original graph are adjusted by subtracting the shortest path weight from the new source vertex to the vertex at the other end of the edge. Finally, the Bellman-Ford algorithm or Dijkstra's algorithm is used to find the shortest paths between all pairs of vertices in the dereweighted graph. Applications of Johnson's algorithm. Johnson's algorithm is used in a wide range of applications, including transportation networks, computer networks, and VLSI design. In transportation networks, the algorithm can be used to find the shortest paths between all pairs of cities, allowing for the efficient routing of goods and passengers. In computer networks, the algorithm can be used to find the shortest paths between all pairs of nodes, allowing for the efficient routing of data packets. In VLSI design, the algorithm can be used to find the shortest paths between all pairs of terminals, allowing for the efficient routing of signals. Python implementation. Import numpy as npdef Johnson, matrix n equals len, matrix, h equals 0 asterisk n for I in range, nhi equals min, matrix ij for j in range, n, for I in range, n for j in range, n if matrix ij.
So again, takes the adjacency matrix, loops over the columns, I think. Let's see. 0, 1. It's the minimum value of each column, I think. That's what this does. Because you're looping through the column and then you're getting that based on the I here, which is gonna be this value, which is the value of the row for the column. So hi is gonna be the minimum value, which is gonna be stored on this, which is the list actually. Then you loop again twice, checks to see if it's different than infinity. If it is, you subtract the minimum value from it again already. That's the part of reducing the weights, I think, that it was talking about. Then it does a Floyd-Marshall thing here. And then it adds the... I'm confused about this part here with this part. I think I understand intuitively how it works, but I'm gonna spend a little bit more time, just like in the previous one, to make sure that I understand and to make sure that this is correct.
This implementation takes as input an adjacency matrix represented as a 2D list, or numpy array, where a matrix ij represents the weight of the edge from vertex I to vertex j. The function returns the shortest path lengths between all pairs of vertices. Conclusion. Johnson's algorithm is a powerful tool for finding...
Yeah, since it is the break, I think that it's a very good idea to just watch a bunch of videos. I roughly understand here the concept. So you're just updating the weights and you're performing a search based on that, but I want to understand more this thing here. Why does it loop here and then it decreases based on the minimum value of the row in the column, which would be... Yeah, it's an adjacency matrix, so not necessarily the neighbor, but it's the row from the column. It stores the minimum value of the row from the column, then it loops to see if it is infinity. If it's different, it subtracts the value of the weight, I guess, from that node with the minimum value that it got here from that row. But then why does it increase after it makes it become the minimum value here. Yeah, this is what I don't understand. I'm gonna watch some videos while I eat something. And I think I'm gonna do the same thing that I did with the other one, where as I clarify the doubts that I have, I'm gonna write, like, I'm gonna explain the article so that someone that has the same doubts that I have understands what's going on. So it's easier for them to understand what's going on. I'll select a few videos here. I think all of these videos are not gonna be the way that I want. And there's a bunch of people making videos like this now. I guess it's pretty common, like use fear to clickbait. And it is kind of a lie. I guess I'll watch this 3 only, or 4. I'll be right back.
Hello everyone, this is Shetty. In this video, we will discuss how to solve the problem on Johnson's algorithm. In the previous video, we have discussed Benencourt algorithm. In that Benencourt algorithm, we are considering some vertex which is present in the graph as a source and we are finding the shortest path. But in Johnson's algorithm, we have to consider the new vertex such that all the weights of that path should be 0. For this graph, number of vertices is 5 and edges are 9. Let us consider the new vertex S such that it should be connected to all the vertices. It should be directly connected to all the vertices which are present in the graph, such that weight of the each path should be 0. Weight of the each path should be 0. Then now the graph will be, we call this graph as V dash, that is V dash and E dash. Okay, where V dash is equal to number of vertices, that is 5. E dash equal to number of edges, 14. Okay. Now we have to find the shortest path from S to all the vertices. Okay, ready? S to A, delta of S to A is equal to, we call this as a H of A. You can also call this as a H of A. H of A is equal to S to A. The shortest path is 0. Okay. Then H of B is equal to delta of S comma B. S to B. S to B. B is here. If you are connecting directly means it is 0. We have to consider this path. S2, that is S to D, then D to C, then C to D, that is 0, minus 5, plus 4, it will be minus 1. This is the shortest path because minus 1 is smaller than 0. Then H of C, H to C, that is S to D, delta of S to S comma C, that is S to C, then D to C. It will be 0, 0, minus 5. It will be minus 5. Then H of D, that is delta of S to D. S to D, it is 0. S to D, it is 0. Directly we can say. Then H of E. H of E, that is delta of S to E. S to E, it is S to A. Then A to E. It will be minus 4. We can conclude that H of A is equal to 0, H of B is equal to minus 1, H of C is equal to minus 5, H of D is equal to 0, H of then A to C, A to C. There is a path is minus 4.
In this video, we'll cover Johnson's very cool algorithm. It shows how to use the reweighting technique we introduced in the last video to reduce the all-pair shortest path problem in graphs that can have negative edge links to a single indication of the Bellman-Ford shortest path algorithm, followed by n indications of Dijkstra's shortest path algorithm. We concluded last video daydreaming about this best case scenario where we have a graph with negative edge links, but somehow we come up with these magical vertex weights that transforms all of the edge links to be non-negative. And it turns out that the magical vertex weights which will realize this best case scenario are best computed by a shortest path algorithm. So before describing Johnson's algorithm in general, let me just walk you through some of the steps in an example. So I've drawn a directed graph with 6 vertices and 7 edges. I've annotated each edge with its cost in blue. Notice that some of the edges do indeed have negative costs, so it is not currently an option to run Dijkstra's algorithm on this graph. There is no negative cycle, however, in this graph. It only has one cycle, the directed triangle at the top, and its overall cost is 1. So we could run the Bellman-Ford algorithm on this graph if we wanted. So our strategy is to compute a magical set of vertex weights so that when we transform the edge links using the reweighting technique described in the previous video, we wind up with a graph that now has only non-negative edge links. So where do these vertex weights come from? Well, the great idea in Johnson's algorithm is to compute them using a subroutine for the single source shortest path problem. To implement this, we need a well-defined instance of the single source shortest path problem. In particular, we need a source vertex. So that's a pretty good idea. There's only one small problem with it, which is that when you pick your arbitrary source vertex, it might not be able to reach all of the other vertices. And to get our magical vertex weights, we're really going to want finite shortest path distances from our arbitrary source to everybody else. For example, in the graph that I've drawn here on the slide, it doesn't matter which of the 6 vertices you choose as your source vertex, you will not be able to reach all of the other 5. So how do we get around this issue? Well, with a simple hack. We're just going to add a new vertex, so a 7th vertex in this example, and we're going to connect this new vertex, which I'm going to just call S, to all of the original vertices with a direct arc of length 0. We are then going to compute shortest paths from this new artificial source vertex S to all of the vertices from the original graph. Notice that by construction, we're going to get a finite shortest path distance from S to all the vertices. We've installed a direct path from S to everybody else. Notice that because this new vertex S has no edges going into it, it's effectively invisible from the perspective of all of the original vertices in the graph G. So in particular, the shortest path distance between any pair of vertices U and V in the original graph is unchanged by this addition of the vertex S. Similarly, whether or not G has a negative cycle is unaffected by the addition of the vertex S. The next step of Johnson's algorithm is to invoke a single source shortest path algorithm using this newly added vertex S as our source vertex. Now, in this example, and in general, we're thinking about the case of negative edge links, so we're not going to be able to use Dijkstra's algorithm to solve this single source version of the problem. We're going to have to use the Bellman-Ford algorithm to do this computation. So let's now go ahead and figure out what are the shortest path distances from S to the other 6 vertices in this graph on the slide. So let's start with the vertex A. What's the shortest path distance from S to A? Well, it's certainly no worse than 0. There's a path directly from S to A of length 0. And indeed, in general, all 6 of the shortest path distances that we compute will be 0 or less. So the question is there a path from S to A that is negative, that's better than 0? Well, what are the other options? We could go from S to C at length 0, but then we pay 4 to get back to A, so that has length 4, so that's no good. A little bit better, but still not good enough, would be to zip straight from S to B, that has length 0, from B to C. Now we're down to -1, but then we have to go from C to A, and so we add 4, so we get 3. So we conclude that the shortest path from S to A is indeed the direct one-hot path of length 0. Most of the other vertices are more interesting, however. Think, for example, about vertex B. We could, of course, zip straight from S to B along a path of length 0, but we can get shorter than that. If we go first from S to A at length 0, and then from A to B, then that path has combined length -2, and that is, in fact, the shortest path distance from S to B. The shortest path distance to C is just to take that same shortest path to B and then concatenate the edge of cost -1 from B to C. That is, the shortest path from S to T goes S to A to B to C for a combined length of 0 plus -2 plus -1, -3 in all. So now let's move to the bottom of the graph. The vertex Z is pretty easy to think about. There's only one path in the entire graph. That's the direct one from S to Z. So Z is just going to have the trivial shortest path distance of 0. So now for the vertex Y, you got a bunch of different options. You could, of course, go straight from S to Y length 0, but there's a lot of things better than that. You can also go from S to Z, and then along the -4 arc to Y. That would give you a path of length -4. But you can do even better than that by going first to A, then to B, then to C, and then to Y. So that gives you a path whose edge costs are 0, -2, -1, and -3. That gives you a combined total of -6, the shortest path distance to Y. Similarly, the shortest path to get to X, the best thing to do is to accumulate all the negative weight at the top of the graph, go via vertex C, and it's true you have to pay the cost of 2 to get from C to X, but you still end up with a net length of -1, which outperforms the direct 0 length path from S to X. And the weights piece of, you define the new length C prime E of an edge E3, as we add 3, so that again all cancels out, and Z comma Y, we start with -4. In this example, the proof is realized that the best case scenario would be you change the origin of the desk, that maybe we have to use the fast edge links, the source vertex, to compute all of the shortest path distances.
So let's look at some of these things, and I'm going to be using the same terminology that I'm going to be using for Dream Machine and so on. Different textbooks.
Yeah, I think I'm going to stay for 1.5 hours more, and then I'll stop.
To use different terminology, but because I want you to become familiar with this terminology, that's what we are going to be using. First of all, JI, job I.
I don't know what happened there in the meditation as well, but I think it's disconnected the OBS, but looks like it's reconnected again.
Right, 1, 2, 3, 4, 5, 6, 7, 8 job problem. Then we will use the terminology AI to represent the processing time on the first machine. A, B, C, D, and so on. AI is the processing time on the first machine. So let's put 5. DI is used to represent the processing time on the second machine. So let's put some numbers in here for. So this is representing a job, 2 machine, low job problem. And for that, we have Johnson's algorithm to solve the problem. The way that Johnson's algorithm works is very, very, very simple. Only 2 steps. First, we have 8 jobs. So the sequence that we are going to be using has 8 slots that need to be fulfilled. 1, 2, 3, 4, 5, 6, 7. So one of these jobs are going to be scheduled here, 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 and so on. The next step is to look at all these processing times, both AI and BI, on both of them, and find the minimum number, the minimum processing time. In here, the minimum processing time is 1 in here, and there's no other minimum. Then, when you find the minimum, based on whether that minimum is on the first machine or on the second machine, you will schedule it in this sequence. For this, the minimum processing time is on the first machine. If it is on the first machine, you schedule that early in the sequence, first in the sequence. So that is J7. So you schedule J7 in here. As you schedule one job, you will eliminate that job from further consideration. Then you will look at the others. There is one job in here, and there is another job in here, with a processing time of 2. This one is an arbitrary choice, whatever you want to select first. It doesn't make a difference in here, as you will see. There's 2 in here, and it is on the first machine. So you will schedule it first. So this is already scheduled. The next slot available is J3. So this is eliminated from consideration. Now you have this job, and it is on the second machine. So it is scheduled last. So this is J6, will be scheduled at the last of the 7. So that's the other. Now it happens that both of them are on the same machine. Then you have a choice. You can either put it here or here. Doesn't make any difference. So the next one, choose on, you have 3 in here, you have 3 in here, and 1 is on the second machine. So we will schedule J2 in here. Then we'll continue this process until all jobs are exhausted. Next one is 4, and we have 2 4s. The next one, 5 on the first machine, and 1 on the second machine. So J1 goes in here, J5 goes in here. Notice that there was another 4, but that's already gone. It's no longer available. So there are 2 more jobs, and this is the minimum. That's the minimum. So J8 goes last, and the last one, of course, is J4. So this is my sequence. That sequence says send these jobs in the same order on the machine. So send job 7 to machine 1. When it finishes, J3 to machine 2. We cannot start both of them at the same time. These were basic requirements that we introduced last time. No job can be processed on 2 separate machines at the same time. No machine can process 2 different jobs at the same time. So these were some of the things that we introduced last time. But anyway, now let's look at the scan chart. Look at chart in 1, machine 1, and 2, machine 2. And this is the first time. Okay. So we're going to schedule the same way again. Job 7 is 1 and 4. So if we finish that, that's J7. And that's J7 on the second machine. And some of the terminology that we want to. What is the completion time? I've already scheduled job 7 on 2 machines. What is the completion time on the first machine? 1. Okay. Completion time on the first machine is 1. What is the completion time on the second machine? It's 5. So it is 1 plus 4, which is 5. Then we'll schedule J3. J3 is 2 and 5. J3 is 2. So it's going to go down here. That's J3. 2 and 5. And 5 is going to go here. That's J3. 2 additional terminology. 1 is idle time. There's no idle time using machine 1 ever. You can schedule it right after each other. On machine 2 is a different story. It depends on when this job finishes. Right now this was 2 and this machine was working. So there was no need for idle time. It just had to wait. It had to wait until the second machine finishes its processing. And the moment that it finished, it was just sitting there waiting for this. So it started its work. So there was no idle time on the second machine. But let's assume that this number was 10. So it would come all the way down here, and this machine would finish, and would wait for the job 8 to come down. So those idle times are very significant and are entered in here. Because this is my last machine. If I enter an idle time here, if I have to incur an idle time here, what happens at the end of the process? It just keeps increasing. So the idea is to avoid idle times. So when you write this in terms of the mathematical programming, minimization is to minimize the idle time. If idle times are minimized, then you have the best decision. So J3 in here. So what is the completion? If I had only these 2 jobs, what would be the completion on the first machine? 1 and 2 is 3. That's 3. And what's the completion on the second machine? Is 1 plus 4 plus 5 is 10. What is that one? That idle time in here that this machine is waiting until job 7 comes down. What is the completion time of the schedule? We only have these 2 jobs. 10. So the completion time of the schedule is the completion after this one. Is 40. And this schedule is off.
I think I'm just gonna use ChatGPT again. And it's the same problem in this video. He explains very well, but it's the same thing where he's just talking about the concept and not showing the translation into code. So I'm gonna use ChatGPT and put some music, and I think I already understand how it works. I'm just gonna make sure. And this one is different than the one that I have here. I think I understand. I was updating the weight based on the distances using Belmont 4. After it updates, it uses the Dijkstra. Let's see if I can do this. Maybe I'll do explain this code first, and then I'll get the specific lines. I'll get this line here. Yeah, so it's removing the negative weights in the first part. That's why it decreases from this value, which is the minimum value. Yeah, but if the weight is negative, isn't it going to add and stuff? is this line here. I got it. So it first removes the negative weights, should then find the shortest paths. And the reason why it adds again is because you want the weights. But you want to find the shortest path, so you have to remove them. And then after that, you add them again. Well, I think I understand. So I'm gonna add this here. I have to spend some time thinking about this. It's getting the minimum value. Oh, the minimum value is gonna be negative. That's why. Let's say there's minus 20, minus 40. Oh yeah, so that because the minimum value, if the minimum value is negative, then it's actually it's gonna make the other negative values positive because they're not lower. That's why he removes them. By adding the other weights that are different than infinity. First, you get the minimum weight for all values and store them at least age. This is done so you can remove negative weights by adding the other weights that are different than infinity with the smallest value. So in the operation, this operation here, the negative weights are removed because if negative weights exist, hi will have the lowest value. When you subtract a negative number, it becomes positive. Because of this, if there are other negative weights as well, they will become positive by adding hi, which was a lower negative value but became positive because the minus operation. I think that's good enough. After removing the negative weights, you can use another algorithm of your choice. In this case, Floyd Marshall, who finds the shortest path from all nodes. After finding the shortest path, the weights are added again to the final nested orbit. Yeah, so this I think can be any algorithm. In this case, it's using the Floyd-Marshall, but you can use any algorithm you want. And then you add the weights back again. Makes a lot of sense. And the principle is the same with the Floyd-Marshall of the thing that you're gonna pass is an adjacency matrix where if the value is infinity, it means that the edge doesn't exist between the nodes, and otherwise it's gonna be the value of the weight. And that's why we make this condition here, because you want to optimize so it doesn't waste time going to the nodes that don't have connections. Negative weight, you can use another algorithm of your choice. Yeah, I'm pretty sure that's Floyd-Marshall, I remember, because I just did that one. Let's look at this one to see if I have the correct thinking. And this other implementation I think is slightly different. Yeah, so here is using Bellman Ford to get the distances first, and then he's using that to remove the weights. Which I understand now. But then it does the same pattern where it finds the distance later and then adds the weights again. Maybe not. This one is only finding the shortest path, but it doesn't add the weights again. Yeah, so I guess it's slightly different. because here is using the minimum value of the row to update the weights, and here is using Bellman-Ford to find the shortest path, and then you're using that value to decrease the weights. I was confused on Bellman-Ford because I confused negative cycles with negative weights. I remember that Bellman-Ford allows for negative weights, and that's the reason why I thought that when I saw that for the algorithm, the implementation, that it doesn't allow negative cycles, I thought it was weird. It was because I was confusing the negative weights with negative cycles. Make the edges of the graph and run these range vertices. So I'm not really sure if it's important to, like, what is the fundamental way to apply it. Because here it's just returning the distances, but here it returns the matrix with the weights updated. So I guess this is an implementation that allows you to run a different algorithm to find the distances, because you're removing the negative weights. And then this one runs an algorithm that already accepts the negative weights first, which is Bellman-Ford. Yeah, but either way, I don't understand why this doesn't put the weights back on after. I guess it's returning the shortest path though, so it's not returning the matrix. I think it's slightly different, but I think the overall principle is to update the weights first and then find the shortest path, and that's the difference between Johnson's and the other algorithms for finding the shortest path. Johnson's updates the weights first, and the other ones are just for finding the path. I think I'm gonna move on to the next one. I don't think it's worth extending too much this one, and I think I'm pretty confident that this is correct, so Johnson topological sort.
Johnson's algorithm is a powerful topological sort. Topological sort, a comprehensive guide. Topological sort, also known as topological ordering, is a fundamental concept in computer science and graph theory. It is a linear ordering of the vertices of a directed acyclic graph, DAG, such that for every directed edge, u, v, vertex u comes before vertex v in the ordering. In this article, we will dive deep into the concept of topological sort and its various applications. What is a directed acyclic graph, DAG? Before we can understand topological sort, it is important to understand the concept of a directed acyclic graph, DAG. A directed graph is a set of vertices, or nodes, and edges, where each edge has a direction from one vertex to another. An acyclic graph, on the other hand, is a graph without any cycles. A DAG is simply a directed graph without any cycles. In a DAG, it is possible to reach any vertex from any other vertex by following the directed edges. This property makes DAGs useful in a wide range of applications such as scheduling, data compression, and solving problems in theoretical computer science. What is topological sort? Topological sort is a linear ordering of the vertices of a DAG such that for every directed edge, u, v, vertex u comes before vertex v in the ordering. In other words, if there is a directed edge from vertex u to vertex v, then u must appear before v in the topological ordering. There can be multiple valid topological orderings for a given DAG. For example, given the following DAG: A-B-C-D-E. There are multiple valid topological orderings such as A, B, D, E, C, or A, D, B,
This
E, C.
doesn't look good, so I'm going to change. This is the wrong line here. Don't know why I did it like that.
There are multiple valid topological orderings such as A, B, D, E, C, or A, D, B, E, C. Applications of topological sort. Topological sort has a wide range of applications in computer science and other fields. Some of the most notable applications include 1.
Oh, I
Scheduling.
think I get it.
Topological.
So it is like that because A should be, you can go through B, C, or you can go through D. A, D, B, C, E. So yeah, I'm gonna leave it like this again. But it is kind of confusing. So I think I'm gonna put A here.
What is topological sort? Topological sort is a linear ordering of the vertices of a DAG such that for every directed edge, U, V, vertex U comes before vertex V in the ordering. In other words, if there is a directed edge from vertex U to vertex V, then U must appear before V in the topological ordering. There can be multiple valid topological orderings for a given DAG. For example, given the following DAG, A-B-C-D-E, there are multiple valid topological orderings such as A, B, D, E, C or A, D, B, E, C. Applications of topological sort. Topological sort has a wide range of applications in computer science and other fields. Some of the most notable applications include 1. Scheduling. Topological sort can be used to schedule tasks in a way that respects the dependencies between them. For example, in a software development project, certain tasks may depend on the completion of other tasks. Using topological sort, we can determine the order in which tasks should be completed to ensure that all dependencies are respected. 2. Data compression. Topological sort can be used to compress data by removing redundant information. For example, in a DAG representing a hierarchical file system, topological sort can be used to compress the file system by removing redundant information about the directory structure. 3. Solving problems in theoretical computer science. Topological sort is used in a wide range of problems in theoretical computer science, such as solving the problem of finding the longest path in a DAG. How to perform topological sort. There are several algorithms for performing topological sort, but one of the most popular and efficient algorithms is Kahn's algorithm. Create a queue and add all vertices within degree 0 to the queue, while the queue is not empty. Dequeue a vertex from the queue and add it to the result list. For each outgoing edge from the dequeued vertex, reduce the in-degree of the adjacent vertex by 1. If the in-degree of the adjacent vertex becomes 0, add it to the queue. If the result list contains all vertices, return the result list as the topological ordering of the DAG. If the result list does not contain all vertices, then the DAG contains a cycle and no valid topological ordering exists. It is important to note that while topological sort can be used to find a valid ordering of a DAG, it cannot be used to find a valid ordering of a general directed graph, i.e. a graph that may contain cycles. In such cases, other algorithms such as Tarjan's algorithm or the strongly connected components algorithm may be used to detect and break cycles in the graph. Python implementation.
So initializing degree of all vertices as 0. And for you in graph. Counting degree of each vertex. So this issue starts, I think, adding them. It's pretty much the same pattern as Braf for search, I think. When it comes to these parts, and initializes everything to 0 first. What is in degree? Yeah, I suspected that it was the case. Because it's directed, you want to know how many connections each one has. And you do that by accessing this V from the graph view. Yeah, and U is the node, I think. So the connections to the node are the V's here, and is creating on this dictionary the key with the value and increasing for each node. So it counts the amount of vertices that are connected to that node. after it has a key for all of them equals to 0. Then adds all of them to the queue. Pops the first one. Top order that append you. Reducing degree of its neighbors by 1. If in degree of a neighbor becomes 0, add it to queue. So what does that mean? Yeah, so now he's reducing the connections after it appended to the top order. And I think it stores the direction based on the top order list. So it's counting the vertices, and then when they reach 0, it appends to the queue. I think I understand how it works. It's not that complicated, this one. So it puts everything on the in the top order, and then after that it goes through the connections and until it reaches 0, and then it appends the current one to the queue so that it goes again, I think.
This implementation first counts the in-degree of each vertex and stores it in a dictionary. It then creates an empty queue and adds all vertices with in-degree 0 to it. The algorithm then repeatedly removes a vertex from the queue, adds it to the topological order, and reduces the in-degree of its neighbors by 1. If the in-degree of a neighbor becomes 0, it is added to the queue. This process continues until the queue is empty, at which point the topological order is returned. Conclusion. In this article, we have covered the concept of topological sort, its applications, and one popular algorithm for performing topological sort, Kahn's algorithm. Understanding topological sort and its applications is crucial for solving problems in computer science, scheduling, and data compression, among other fields. It is a fundamental concept in graph theory and a powerful tool for solving.
I think I'm not going to spend too much time on this one. It seems very simple. I don't see. Yeah, because if it became 0 is the end of the connection there, I think. So it has to explore from that node. Because previously you increased by the number of in degree. The number of vertices to that node. Yeah, it's reducing to see which one gets to 0 first, I think. Or each one gets to 0 because that's gonna be the one that is at the end of the connection there. From the specific node. And then from that node, it is obviously going to visit the neighbors. So it gets to the end of the line, let's say, from the neighbors of the current node, and then because once it gets to the point, it appends to the queue whatever that node is, and then it does a process again, and then it returns the connections. I think I understand, and I think it's correct, this thing here. So now, do I put? I don't think it's worth putting anything here though. And that's the thing that I talked about in the beginning, that I'm not really sure what to do. Like I'm still thinking about this, what I'm gonna do, because a lot of these articles, like, it's obviously not great if I leave it like this because it's mostly ChatGPT. But what else am I gonna put here? Like, I can think about good ways to keep the article close to the truth of whatever it is, while changing the whole information, like the words that I'm using, the way that it is describing things, and also maintaining a good level of SEO. Because I can change this stuff, but then it might become like, I can think about different ways to say the information, and it still represents whatever this is to the highest degree of truth, I think. So I don't know. I have to think more about this, like what I'm gonna do, if I'm gonna do. Because the thing is, like I said before as well, everyone is gonna use this stuff, so you're kind of forced to use it. So, but it's definitely a gray line in my mind. I'm not really sure. I could ask myself what I would do if all this information wasn't here. But then, like, what's the point of using the tool in the first place? And even if I'm sure it would be different if I wrote it down. But then after seeing this, it's kind of like, it's this weird thing, because it's even with, let's say you're not using ChatGPT, but you're using a search engine. Like, it doesn't matter which way you go about it, the information, like, you're gonna be getting the information from someone else, and it's difficult to think about what is the boundary of authenticity. I think that's the challenge. Like, what does it make it unique? Because especially in a topic like this, where it's just graphs, algorithms, because these are solutions to known problems that have been around for a long time, and a lot of people talked about them already. So I'm not really sure if I should spend time on each one changing a bunch of things just for the sake of changing, even if the information is true or seems to be very accurate based on the fact check that I'm doing here. Or if I should just do a bunch of them and keep going the way that I'm going now. And obviously I'm gonna add the articles that I talked about as well, where, like, new articles where I integrate a bunch of information. And I think that's the best approach that I have in my mind right now, which is to use this first as the baseline of the funnel, let's say, and then work. It's kind of like a filter for AI of parsing the information, and also after parsing the information, to have a high degree of accuracy, then using all the information and synthesizing it to come up with new things that combine everything into one thing. But besides that, I don't know if I should or I shouldn't try to change these articles too much just for the sake of changing them, the way that they are wrote. Yeah, I think I'll have to think more about this. I'm gonna keep going like this for now, but I'm not really sure about it. It's very gray for me. It feels it feels kind of, because I don't know for sure if what I can and can't do. Like that's the problem, is that there isn't a clear line of what's acceptable and what's not, because the AI model is built on top of a bunch of data, and like how do you determine what's copyrighted? It would be different if I was getting the information from someone else, like copying someone else's article and pasting. I think that's very clear that is not correct, and I wouldn't do that, obviously. But then is that this weird thing, because with ChatGPT, like the moment that you have something like this and they make it available for someone, then it kind of forces everyone to use it, because if you don't, you're gonna be behind. But then like they can claim that you're copying their information, and that's the problem, because that's what doesn't make any sense to me, because they are using the information in the first place. That's the only reason why the machine learning model exists, and it's not like it's their information. Like it is, but it isn't in a way, because like I said, the infrastructure forces everyone to use these systems, and then it's like a fake choice, and then they can use all this data to create machine learning models and manipulate everyone. So it's kind of hard to think about. And I think there isn't a very clear answer to this already, like on a legal perspective of what is allowed and what is not allowed. That's the main thing that I'm concerned here. Like, what is the boundary of what is acceptable and what is not on something like this? And maybe at some point I'll delete the text and then just write whatever comes up in my mind. But the thing is, because that's the issue, even if on the stuff that I'm doing with programming and creating websites and things like that, like I'm never gonna be able to come up with everything off the top of my head. Most of the time, everyone that is programming knows this, is that you're always gonna look for stuff on the internet, and even if you do, you say, well, that's not true, like I don't search a lot on Google, but you did before, and that's the point. Like you only don't search because you updated your subconscious with enough data that you don't need to search anymore. But the origin of the data is the same, because it comes from the internet. And if you don't use the internet, then you're obviously behind, so you're forced to use the internet and use the data. But then at the same time, like I can understand, for example, if you just copy what other people do and you put on your page, that's obviously wrong as well, because then you're not doing any work and you're just stealing everyone. And this is the reason why it's so hard for me to make a decision on this. Because with the AI model is different, where the line is not clear, because I don't know where the output is coming from. Yeah, I think I have to spend more time. I can't make a decision now. Like part of me thinks that I should just delete all of this stuff and then just keep with these topics here, and then go from scratch from the topics and write whatever I think about. And then part of me thinks that this is fine, like to review, because what matters is the accuracy of the information. And because if I don't do this, then like everyone else is gonna do it, and I'm gonna lose to them because they are doing. So I'm not gonna be able to produce as much content, and all of this content is gonna help the unique content as well, because of the thing that I talked about, where it generates gravitational force. Like when you go into a website and there's a bunch of different articles and different things, like the chances of someone spending a lot more time on the website is a lot higher because there's a lot more stuff to look at. But if I only have articles on one topic, then it's kind of you're going to spend less time. And obviously with artificial intelligence, this is rising exponentially. Like next year it could be a lot more, it's gonna be a lot more powerful AIs and things like that, so speed matters a lot, I think. So I can't just wait for 2 years to do the articles manually, and because everyone else is gonna do articles with AI, and then if you don't do it, then it's kind of like being in an ocean and then there's a tsunami coming. There's nothing you can do. Like, yeah, so I think I'm gonna keep it like this for now. I'll think more about this. Yeah, if anyone that watches this video has opinions on this, or I would be happy to listen to feedback and to help me make a decision on what is the best way to go about it.
Unlocking the Mystery of Strongly Connected Components, A Beginner's Guide. Introduction to Strongly Connected Components. In graph theory, a strongly connected component, SCC, is a subgraph in which every vertex is reachable from every other vertex. In other words, it is a subgraph where there is a path between any two vertices in the subgraph. In this article, we will dive into the concept of SCCs, their properties, and algorithms to find them in a directed graph. Properties of strongly connected components. A strongly connected component is a maximal subgraph that is strongly connected. This means that it is not possible to add any vertices to the subgraph without breaking the property of strong connectivity. Additionally, any two vertices in an SCC are connected by a directed path in both directions. It is important to note that a directed graph can have multiple SCCs. In fact, the set of all SCCs of a directed graph forms a partition of the vertex set of the graph. This means that each vertex in the graph belongs to exactly one SCC. Tarjan's algorithm for finding strongly connected components. One common algorithm for finding the strongly connected components of a directed graph is Tarjan's algorithm. This algorithm uses depth-first search, DFS, to identify the SCCs. The basic idea of the algorithm is to perform DFS on the graph, keeping track of the vertices that have been visited and the order in which they were visited. The algorithm starts by initializing a stack, a visited array, and a low-link array. The stack is used to keep track of the vertices that are currently being visited, while the visited array is used to keep track of which vertices have been visited, and the low-link array is used to keep track of the lowest vertex that can be reached.
I think the solution has to be on a systematic level, because if it continues like this, there is no incentive for anyone to create anything, I think. Because the AI is only gonna get better and better, and then the moment you do something original or unique, it's gonna be scraped through a bunch of AIs, and then people that are using automated content are gonna win anyway because they are not making the effort of coming with the creativity. So, yeah, like I think there must be regulation, I think, on the AI, so that there is somehow a way for them to add credit or to reward people for finding original ideas or writing original stuff, whatever that means, because obviously there's nuance. But otherwise, I don't see, because then what's the point of creating any content if it's gonna be scraped automatically, and then someone with more money is gonna rank higher because you can just spend on AI and then do it much more efficiently.
while the visited array is used to keep track of which vertices have been visited and the low-linked array is used to keep track of the lowest vertex that can be reached from a given vertex. The algorithm then proceeds to perform DFS on the graph, starting with each unvisited vertex. During the DFS, each vertex is pushed onto the stack and its low-link value is set to the index of the vertex in the DFS order. As the algorithm explores each vertex's neighbors, it updates the low-link values of the neighboring vertices if necessary. When a vertex is finished being explored, the algorithm checks if the vertex is the root of a strongly connected component. If it is, then it pops all the vertices on the stack that belong to the SCC and adds them to the list of SCCs. Kosaraju's algorithm for finding strongly connected components. Another algorithm for finding strongly connected components is Kosaraju's algorithm. This algorithm also uses DFS, but it utilizes two passes to explore the graph. The first pass of the algorithm is a DFS of the original graph, which creates a stack of all vertices in the graph in the order they are finished in the DFS. The second pass is a DFS of the transpose graph, where the edges are reversed, and the stack from the first pass is used to determine the order in which the vertices are visited. During the second pass, each time a new vertex is visited, it is added to the same strongly connected component as the vertex that immediately precedes it on the stack. Applications of strongly connected components. Strongly connected components have many applications in computer science and other fields. Here are a few examples. Compilers. In compilers, strongly connected components can be used to detect loops in a control flow graph. A loop is a strongly connected component in the control flow graph where the entry and exit vertices are the same. By identifying these loops, compilers can optimize the generated code by eliminating unnecessary computations and improving performance. Model checking. In model checking, strongly connected components can be used to reduce the state space of a system. A state space is a set of all possible states that a system can be in. By identifying strongly connected components in the state space, the model checker can avoid exploring the same states multiple times, reducing the number of states that need to be considered and improving performance. Program analysis. In program analysis, strongly connected components can be used to detect and eliminate infeasible paths in a program. An infeasible path is a path in the control flow graph of a program that can never be executed. By identifying strongly connected components, program analyzers can eliminate infeasible paths and improve the accuracy of the analysis. Python.
I think I'm gonna stop here because I'm already tired. I think I'm gonna take a break and then do the rest of this off stream. I think I'm gonna try to do 2 or 3 more today, or maybe 4. I think I'll do some exercise. 2. Yeah, there's 10 more, so I'm halfway. So if I do 4 more today, I think that's tomorrow I finish this. And then start the 3 ones.
This implementation takes in a graph represented as a dictionary, with each key as a node and its value as a list of its adjacent nodes. It returns a list of lists, where each sublist represents a strongly connected component in the graph. Conclusion. In this article, we have discussed the concept of strongly connected components and their properties, as well as popular algorithms for finding them. We have also explored some of the applications of strongly connected components in computer science.
I think what I will probably do most likely is after I have a book of articles on all of the categories, then I think I'm gonna review them and change things. But I really don't know like how to find the line there, or what kind of stuff to write here. It's not clear at all, I think. It's either way you're already in a disadvantage, I think. I have to erase this. I just did these articles here to have something to test for the routes. Yeah, but I wanna have a bunch of articles for each category first. Then I think I will change the articles after that. But I don't know if I will change them. That's the thing. Because it's gonna be very hard to come up with a different way to say the same thing. and I'm probably gonna have to search for an AI tool to rewrite it as well. Yeah, not sure. So I think I'll stop here, probably come back tomorrow and finish these graphs here if I don't finish off stream. And then next I'm gonna create the articles for trees. I might create the articles for trees now off stream and then review them on stream, because I'm just gonna be using ChatGPT if it's available to create the trees as well, and then just change stuff according to what I think will be make the article better, if there are things also fact check this stuff. And yeah, I'll think more about it if I should change drastically change the structure here. So yeah, see you